Okay, so thank you all for joining us today. I think you're in for a real treat. We're going to have a whole day of excellent talks by the members of the GMN, our scientific collaborators, and the amazing people who are using GMN data in their research. The GMN has finally transitioned from a period of manic growth to a period of sustainability. Our infrastructure has been greatly improved and requires minimal maintenance, relatively speaking. Some kinks are still, some kinks still remain to be polished, but we have a team of talented members and students working hard to make that happen. Now we can focus on scientific analysis of the data set, as well as broadening the scope of the project to help solve some really hard global problems. And I'm going to tell you something about some, highlights of the talks that you will hear today, chosen in a way to draw your attention. So the first talk today is going to be about a very hot topic, interstellar meteors. I think interstellar meteors are always a hot topic. Professor Paul Wiegert and his student Vanessa Tran led the effort to analyze GMN data in search of this holy grail. Spoiler alert, no statistically significant interstellar meteors were found as of yet, but the search is still ongoing. Then we're going to have a talk about the age of the Gemini meteor shower as measured on GMN data. Now, the Geminids are surely going to start getting more attention as their parent body, the asteroid Phaethon, will be visited by Destiny Plus mission in the early 2030s. And then we're going to hear about a very interesting grazing meteor, which produced an infrasound signal, which is a very rare occurrence for a meteor at such a high altitude at over 90 kilometers. And this meteor can also tell us something about the nature of meteor fragmentation, which is something that everyone is trying to get at. And then we're going to have another talk. So in the last few years, there's been a lot of interest in monitoring variable stars with GMN cameras. So Damir Shigon has made a significant progress in this regard, and so we may soon be able to contribute to that branch of astronomy as well. And then in the second session, so last year, members of the GMN from New Zealand recovered a meteorite within 30 minutes of the search, and the rock was found exactly where predicted. And we'll hear more about it in the second session, which I do understand for some of you it's going to be too late, but the meeting is going to be recorded, so you can always watch it later. And finally, we're going to have Luc Busquin, who's going to tell us about the developments in the GMN's effort to observe contrails and help shave off 2% of climate change impacts, which is a bit outside of our initial meteor mission, but it is most welcome. And we've also been facing challenges of a different kind. So due to global instability, we're planning to move towards a fully decentralized and redundant trajectory processing approach. So you can think of it as our website having a mirror. The idea is that the central GMN server still receives all the data, including images, but several smaller servers around the world will receive only the metric measurements, so the FTP detect info files, which are quite small. And those servers would then give tasks to remote processing nodes, and those can be any computers that have spare computing that will compute the trajectories and send back the results. In this way, we can ensure that there is no disruption of data processing and the real-time reporting. We're going to have Mark McIntyre say more about this in his talk. Now, looking back a few years ago, I called GMN a radical experiment in diplomacy, and we're trying to bridge over regional, global, and the hardest of all, interpersonal differences. And this mission is still central to the GMN. So finally, I would like to thank all of you who have contributed to the network, either with funds, time, or simply goodwill. I hope you stick around with many years to come, and I declare the meeting open. And we usually start the meeting with with a round of introductions, which is going to last for about 10 minutes. I usually introduce myself. So I'm Dr. Dennis Vida. I'm an adjunct professor here at the University of Western Ontario, and I like meteors. So who would like to go next? And I would ask you to raise your hand in Zoom, and then as you raise your hand, I'm gonna, see that on the participant list, and I'm just gonna call out your name, and then please introduce yourself briefly. Okay, so we have Tim Cooper. Tim, go ahead.
Hi, I'm Tim Cooper. I'm in South Africa. I'm involved with the GMN's outreach project, placing cameras at schools. We've put 4 cameras into 2 schools last year, and we're planning on expanding the network during 2025.
Thank you, Tim. Okay, so Mark, go ahead.
Yeah, I'm Mark McIntyre. I'm based in the UK, and excuse me, I'm part of the UK Meteor Network, and I'm also Meteor Section Director for the Society of Popular Astronomy here in the UK.
Thank you, Mark. Next up, we have Dino. Dino, go ahead.
So, hello everyone, I'm Dino Grzinic, and I joined the Global Meteor Network last year and have since worked on a couple of projects, some of which I'll be presenting today. I'm currently in my third year of college, studying computer science, and I also like astrophysics.
Amazing. Thank you, Dino. Oriane, go ahead. Oh, Oriane, you're muted.
Yeah, sorry, I'm just waking up. So I'm Maureen Gall. I'm a researcher at the Planetarium of Montreal and also an adjunct professor at Western University, and mostly interested in dynamics of meteorite streams, meteorites, meteors in general.
Thank you, Oriane. Okay, so Paul, go ahead.
Thanks. Excuse me. My name is Professor Paul Wiegert. I'm at the University of Western Ontario as well in the Department of Physics and Astronomy and excuse me, the Institute for Earth and Space Exploration. We're going to talk about some of the interstellar results that GMN is producing. Very excited about all the high quality data coming in from GMN and very excited to be participating in this conference.
Thank you, Paul. And then we have Jamie Shepherd. Jamie, go ahead.
Hi from Scotland. I've been a meteor nut since I was a boy, and my particular interest is in analysis, trajectories. I just love that stuff. I love all the maths, the physics, the measurements. It's just the most amazing hobby, and I hope to share some of that with you later.
Amazing. Thank you, Jamie. And then Teddy. Teddy, go ahead.
Hi, I'm Teddy Coretta. I'm a postdoctoral researcher at Lowell Observatory, and I think in 2 hours, something like that, I'll be talking a little bit on how to compare data from the GMN to actual telescopic observations of the same objects before they touch the atmosphere. So I think it's a cool topic, and I hope you guys get a kick out of it.
Awesome. Thank you, Teddy. And Marco, go ahead.
Hello everyone, I'm Marco Shagon, and I'm finishing my PhD. Currently, I finished my work at Andrzejew Observatory in Prague under Dr. Jiří Borovička, and I'm working on meteor spectra, just as I said, finishing my PhD in that regard, and haven't done much GMN work so far in the last few years, but hopefully once I'm finished with the PhD, I'll have some time to join in with the work.
Awesome. Thank you. And we have Edward Cooper. Go ahead.
Hello. Hello. I'm calling from Wales. I am also associated with the GMN Schools Network project. We've got two cameras in one school. There are another 6 cameras that sit in schools awaiting to be put on buildings, but that's very frustrating. It doesn't seem to get the attention that one hopes it would. I've got 9 cameras I look after in total for the UK, and that's me really.
Awesome. Thank you. And next up, we have Elizabeth. Go ahead.
Hi, my name is Elizabeth Silver. I'm Western University alumni. Spent some time there working on meteor physics. I'm now a scientist at Sandia National Labs, and I still continue my collaboration with Western University. In fact, I will be talking about a rare Earth grazing fireball, collaborating with Dennis and Jamie. So that's it for me.
Awesome.
Thank
Thank you
you.
so much, Elizabeth. Rob Steele, go ahead.
There we go. Unmuted. Rob Steele from California. I'm up in the mountains up there and gotta working with some schools, trying to work with some schools. Sometimes some people know that's frustrating. I'm retired from JPL, where I spent 30 years as a software engineer, and been an amateur astronomer basically my whole life. So this has been a fun project to be part of.
Thank you, Rob. And next up, we have Gulchera. Go ahead. We can see you.
Good evening, everybody. I am Kohirova Gulchekra. I am from Institute of Astrophysics of the National Academy of Science of Tajikistan. It is my first participation in this meeting, and I will provide more detail about our activity during my presentation. Thank you.
Thank you. Next up, we have Danila Milano. Go ahead.
Hello, I'm Danilo Milanov. I'm a researcher from St. Petersburg University. My fields of interest are metrics in the space of Keplerian orbits and figures of equilibrium. And now I reside in Montenegro. That's it. Thank you.
Thank you. Next up, we have Paul Rogermans. Go ahead.
Hi, I'm Paul. I'm 50 years involved with meteors now, and in fact, since we are using these video cameras, I see everything coming through what we were hoping for in the 70s and 80s and were unable to get. So there is so much data in this database, Orbit database from GMN, that I'm very much looking forward to do more analysis on it. It's really extraordinary, the quality of the data and the quantity of the data to do what we have never been able to do before. Thank you.
Thank you so much, Paul. And next up, we have Logan. Go ahead.
Hi, I'm Logan. I'm a graduate student at the University of New Mexico, planning to defend here soon at the end of the semester. My research interest is in long-lived meteor trails, which is what I'll be presenting on today.
Awesome. Thank you, Logan. Do we have any more takers? Okay, Luke, go ahead.
Hi, I'm Luc Busquin from Phoenix, Arizona. I'm an airline pilot interested into reducing the climate impact of aviation, and I will be presenting our contrail observation project later on.
Amazing. Thank you. Anyone else? Let's see. Gaetan, go ahead.
Hi, my name is Gaetan Laflamme. I live in Quebec, in Canada. So I have two camera operating, and I help other guys in Quebec to support everything. So I like this project. Thank you very much.
Thank you. And then Pete Ashman, go ahead.
Yeah, my name is Pete Ashman. I try to coordinate the local meteor network. We call ourselves the New Mexico Meteor Array, and we have about 29 cameras, but I'm also trying to help out with some folks in California and other folks as needed.
That's amazing. Thank you. And I was also asked by someone who couldn't make it to the meeting. So I'm going to play their short introduction, if you don't mind. I'm going to share my screen here. Let's see. Let's do it like this. And let's see if this is going to work. I think I need to share my sound.
Member of the Hungarian astronaut.
Okay, sorry about that.
Hi, my name is Ben Takish. I am a member of the Hungarian Astronomical Association. On suggestion by Gábor Süle, last year we have successfully deployed a now 3-camera system at our remote observation facility, doubling the cameras in Hungary for the GMN. About me, I am a computer network professional.
Okay, there we go. Does anyone else want to introduce themselves? Let's see, where is my list? Have one more minute. And if we don't have any takers, I'm just going to ask people from the list to introduce themselves. Okay, Kees, go ahead.
Yeah, hello everybody. I'm Kees from the Southwest Netherlands, camera operator for GMN for a couple of years now. My profession is also a pilot, but then on the rivers, the Westerschelde. But I like to hack some cameras into each other and do some more hacking and thinking about putting things together to help the Meteor Society forward. Thank you.
Awesome. Amazing. And that's time. We can continue our introductions and chats during our breaks and in breakout rooms. But now we have Professor Wiegert with his talk about interstellar meteors. So, Paul, go ahead.
Okay, thanks, Dennis. Very happy to be here. So I'm going to share my screen. See if we can get this. Okay, can everybody see that? Does that look good?
We can see our screen.
Okay, well, thank you very much for inviting me to talk here today. So I'm going to talk about a search for interstellar events in the GMN database. So we're very excited about the GMN data. And what I'm going to be talking about here is a study that was performed by myself, Vanessa Tran, Cole Gregg, two students, and Dennis, of course, and Peter Brown, another professor here at the University of Western Ontario in Canada. So why are we excited about interstellars? Well, they're so potentially exciting. Of course, we could get material from other places in the galaxy, other star systems, supernovae. Who knows what other galactic systems we might actually be able to get sort of free samples from to study up close. So we're very excited to try to find these objects. So how do you do it? Well, the best way, or the most direct way, is to look for objects which are traveling at high speed with respect to the sun. The reason for that is that objects in our solar system cannot travel more than about 42 kilometers per second near the Earth relative to the sun and stay on a bound orbit to the sun. And so if they're traveling faster than 42 kilometers per second relative to the sun, when we see them in the Earth burning up in the Earth's atmosphere, that's a strong indicator that they could have come from outside the solar system. Not 100%, and I'll talk about that in a second, but that's how we look for them. We look for things that are moving fast relative to the sun. And so GMN has a fantastic database for looking for these kinds of objects, and that's what I'm going to talk about today. So first, we'll answer that question. Could something from our solar system be traveling at these high speeds? And there are a couple of rare possibilities. One is called a beta meteoroid, and this is when a fast-moving particle in our solar system breaks up near the sun, and then radiation pressure from the sun kind of gives it a boost. And so then it can kind of get pushed onto these higher speed orbits. But these are really only small particles that GMN doesn't see. They're not going to be an issue. It's also possible for a particle like an asteroid passing near a planet to get sort of gravitationally slingshot onto this kind of orbit. This doesn't happen very often, and we can determine if this happened or not by sort of following the meteor's trajectory backwards. So we have the meteor's trajectory from GMN. We can kind of go backwards and see if it passed near a planet, and that will tell us if this is what happened. So we can deal with all of these situations, even though they're kind of rare. So we'll jump to the punchline here. Are there any meteors that were seen by GMN that could be interstellar? Could be, maybe yes. But ultimately, there are no events that were found in the database that were conclusively on escape orbits with respect to the sun. That is, we can be really confident at the 95% level that they were unbound from the sun. But we're not done. Interstellars are going to be found by GMN. They're going to be seen at some point. What we did in this study was just scooped off the top 60% highest quality events. That makes our work a little bit easier. It allows us to sort of sharpen our tools, better understand the data so that we can come back and dig a little bit deeper and see if there's maybe something else in the database. And of course, as GMN continues to accumulate events, eventually we're going to see one. So this slide you're not supposed to read, but these are sort of the quality filters that we put on there. So the reason we reduced it to the top 60% is that you always have some events that aren't as well measured as others. And so we want to try to take the best measured events. And there are lots of them, so this doesn't hurt us. Again, you don't need to worry about the details here. The main filter that we put on is we only looked at events that were traveling relatively slow in the Earth's atmosphere, that is less than 50 kilometers per second. But there are meteors that we see up to 72 kilometers per second. The reason we exclude the fastest ones in our atmosphere is because they tend to have just a few measurements. They're just visible in a few frames. And so they tend to cause a lot of problems. They're harder to deal with. Now, you might say, if you're looking for high-speed events, isn't excluding high-speed events a bad idea? And the answer is that we exclude events that are high speed in the Earth's atmosphere, but not events that are high speed with respect to the sun. And that's because if the Earth is moving as it goes around in its orbit relative to the sun, which is on the left there, some meteors coming from the front hit us at high speed. They hit our windshield. They get run over by the Earth. And these are the ones that are more difficult to deal with. But a meteor traveling the same speed which comes up behind us kind of has to run to catch up with us. And so those may be traveling quite slowly in our atmosphere. So an interstellar meteor is fast with respect to the sun, but does not have to be fast with respect to the Earth. In fact, it can be as slow as 13 kilometers per second with respect to the Earth. So what did we do? Well, we took about 2 million events. After filtering for the quality, we got about 15 million events. And we whittled it down, picking the best ones, the most convincing events, and we ended up with 13 events that we wanted to do a full manual solution. So GMN automatically produces some determination of the speed. The manual solution is when a human operator goes in, looks and sees, okay, are clouds in the way? Do we have enough stars? Is everything okay? And these 13 events, even though they did have automated solutions that were hyperbolic, that is on escape speeds with respect to the sun, once a human operator went in and made the measurements more carefully, unfortunately, they were all consistent with solar system meteors, though a few did have a slight probability of being interstellar. None of them were really strongly, convincingly so. And so, sort of what happened? Well, why were the GMN automatic solutions not good? Well, in fact, they typically were good. They were just off by a little bit. It doesn't take much sometimes to make that difference. But the real world is complicated, of course. The sky is not always clear. You don't always have a lot of stars. There might be clouds, aurora, there are aircraft, spacecraft, other things. And so the automatic picker tries hard, but sometimes it just doesn't work out. Sometimes meteors are far from the cameras, they fragment. Occasionally, we even had two separate meteors seen in different cameras that were almost traveling on the same path, which makes it very confusing. So unfortunately, there are lots of things in the real world that can mess things up. So I don't want to take a lot of time, but if you want to ask me questions about this table gives more information on those 13 events we reduced. But the long and the short of it is they were all ultimately, so this is the automatic speed here on the left. This is what we had after manual reduction. And we had one very exciting event. It was just barely on the limit, an eccentricity of 0.999 plus or minus 0.006, but they're all unfortunately consistent with solar system meteors. This is the fastest events we found, and we just sort of plotted them here on the sky. So this is a projection of the sky together with a few meteor showers on there. And you can see they're not really associated with any meteor showers. They're not associated with the galaxy particularly. This dashed line here is actually the galactic equator. And you can see they don't really concentrate in any particular pattern around the galaxy. They're quite consistent with just occasional measurement errors that make them look like they're traveling faster than they actually are. So what's next? Now that we understand the data a little bit better, we kind of sharpened our tools, and we have to go back again and dig a little deeper and see what we've got. We're convinced interstellars happen occasionally. GMN's going to see them. We just have to be careful. We have to be patient. We have to wait for them to arrive. And it's not that GMN didn't do a good job. In fact, it did a really, really good job with most events. It's just unfortunately that the few events that weren't so well measured had a tendency to look interstellar. So GMN is actually going to do a fantastic job of measuring interstellars. And you can ask me why for more technical details about why this is sort of a hard problem. But even without interstellar detection, GMN has already contributed. This is sort of a more or less technical plot, but on the bottom axis is the mass. And at the left-hand side, we have measurements of very small interstellar particles, which are well known. And then at the far right-hand side, we have the very massive interstellar particles like Oumuamua and Comet Borisov, which are also well known. And then in the middle, we have this twilight zone where we have very few measurements, very hard to make measurements, very few reliable measurements. And GMN is putting solid data points in this sort of twilight zone there. And you can see in the orange area where the GMN line is, and it's close to this theoretical model, which is we're very excited and trying to confirm or refute. GMN is going to do this in the next few years. So GMN is really doing fantastic work. It's sort of right where it needs to be to contribute to this problem. So that's it for me. This work is actually going to be published, hopefully, as a scientific journal. You can see the title there. And I especially want to thank all the GMN operators. GMN does great science, and the only reason it does great science is because of all the fantastic people who are operating the cameras and supporting the project. So we're going to try to acknowledge you all in our paper by name. So look for that when it comes out, hopefully in a few months. So thank you very much.
Amazing, Paul. Thank you for the talk. We have time for one short question. Does anyone have a question? Teddy, go ahead.
Hey, Paul, that talk was great. In the plot that you showed on the second to last slide, comparing all the measurements against the expectations, that you have that dashed line there for the theoretical model. But the fact that all those data points are now landing above that theoretical model, what does that tell you about the flux of interstellar material into the solar system?
Well, we haven't really measured as well as we would like to at this point. But even the theoretical models are, it's hard to know until you actually made your first measurements what you're expecting. So this is a theoretical model from Murray et al. 2004 for, debris disks. For those of you who know something about a protoplanetary disks or remnant debris disks. But there are other sources of particles possible. Asymptotic giant branch stars, young stellar objects, and things like that, which are not plotted on here. So we need to keep taking measurements, but you can see the GMN dot is not that far above the line. I think GMN is going to push its dot down into that line and confirm or refute that prediction soon. So we just need to keep taking measurements.
Amazing. Cool. Thank you, Paul. And next talk is Gulchera. Go ahead. To unmute. There we go. We can see your screen and you're good to go anytime.
Okay. Is it okay, my screen?
It looks great. Go ahead.
Okay, I can start?
Absolutely.
Okay, thank you very much. Let's start our presentation. Generally, astronomy has significant historical roots in Tajikistan, and this is indicated by astronomical data from Avesta book, astronomy from Samanid period, and so on. Present-day astronomical science in Tajikistan originates from Tajik Astronomical Observatory established in November 1932. Geographical position and astronomical climate of Tajikistan correspond to best observations conditions. So in 1958, Tajik Astronomical Observatory was transformed into Institute of Astrophysics of the National Academy of Science of Tajikistan. Astronomical studies cannot be performed without observations. So during short historical period, two modern astronomical observatories with excellent astronomical climate have been built in Tajikistan. They are Hisar Astronomical Observatory, Sangloh Astronomical Observatory, and later in 1995, by the decision of the government of Tajikistan, Pamir Observatory has become branch of Sangloh Observatory. Meteor astronomy, including meteor observations, has traditionally been one of priority areas of space research in our institute. Foundation of meteor astronomy was laid with establishment of the institute in 1932, and it was significantly developed under the leadership of academician Pulat Babajanov. This leadership led to creation of a globally recognized school of meteor astronomy. Meteor observations play an important role in formation and development of this area. Meteor patrol for photographic and spectral observations was put into operation at the Hisar Observatory, including the method of instant photographing of meteors, which made it possible for the first time in the world obtain instant images of meteors and their spectra, and establish the fact of fragmentation of meteoroids. Here, for the first time, simultaneous photographic and radar observations of the same meteors were carried out. Long-term photographic, spectral, television, radar studies of meteors have provided extensive information about radiance, velocities, masses, density, porosity, and orbits of tens of thousands meters. In 2009, in order to study variables and destruction of large meteoroids in the Earth's atmosphere, a photographic variable network was created in Tajikistan. It was the first and only one in Central Asia. The network consisted of 5 observation stations equipped with variable and digital cameras with fish eyes lenses. Systematic photographic observations of variables were carried out in all clear nights simultaneously at 5 points, 2 points in Hisar and Sangloh observatories, and 3 another in Rasht, Hovaling, and Kurgan-Tube villages in Tajikistan. Based on results of observations, we have published 2 catalogs, or one catalog of data of photographic meteor observations carried out in institute during this period, and the second catalog contains results of variables observations in Tajikistan. With the development of technology, observations methods are also improving. Currently, video cameras are widely used in the world for meteor and fireball observations. And on this basis, extensive observation networks are created and operate in United States in America, Europe, Canada, Japan, Australia, and other countries. These networks have already provided a large volume of meteor data, namely over tens of millions trajectories, orbits, radiant masses, and so on, which are subject of separate studies. A significant contribution of networks operation in establishing of new showers and the confirming activity of known showers should be noted. However, meteors occur always and everywhere, so expansion of networks by increasing the number of observation points and placing them in different geographical locations remain to be one of the most important tasks of meteor astronomy. In particular, under the leadership of University of Eastern Ontario, Global Meteor Network operates, and the main goal of which is to observe the night sky every night of the year from as many points as possible, as possible around the world. Observations use low-cost CMOS video cameras with RPI type computer. In the fall of 2023, the head of GMN, Dr. Denis Vida, proposed us during our discussions to place video cameras in Tajikistan. Meteor observations have always been of great importance in the activities of the Institute, and we have constantly strived to restore them to a modern level. As a result, 2 sets of observation equipment were delivered to Tajikistan, to our institute, in the spring of 2024. During May-June 2024, one set of video camera was installed on the roof of the institute building in Dushanbe, and the second set in the Sanglo Observatory. To check the correct installation and direction of the cameras, test observations were carried out at 2 points, during which necessary corrections were made. As a result, on June 9, the first light was received from video camera in Dushanbe, and the first light was received from a camera in Sanglo Observatory on June 19. Main parameters of geographical location and the meteor cameras are summarized in this table.
Bashar, we are slightly over time. Would you mind wrapping up in the next minute or so?
Okay, so how much time I have?
We're already a bit slightly over time, so try to be as fast as possible, if that's okay. Just
Okay,
a minute or two, if you don't mind. Thank you.
Oh, I try to speak quickly. So this is area viewing of our 2 cameras. Cameras are registered in GMN web page and obtained this designation. So astrometric and photometric reduction is known for participators of this conference. Details are provided at these papers. Here I present example of astrometric reduction of 1 hour images And here, example of photometric reduction of our images. So orbits and trajectories are calculated using Monte Carlo method, which also is described at this paper. And brief preliminary results. During this period, we have captured and have calculated orbits, radians and orbits for more than 3,000 meters. Here I present examples of our images obtained from 2 cameras, and you can see examples of light curves for this fireable meteor, for another one, and this also one light curves for one of our detected meteors. And interesting fireable was registered in July 11 last year. You can see images of this fireable here. We obtained reduction of images obtained with, for example, you can see here plot velocity versus time and altitudes, light curves of this fireable. Radiant and orbit are summarized at this table, and according to Tisserand parameter, orbit of a fireable is classified as a typical comet-like, and this fireable is classified as sporadic. So a few words about activity of Perseids from last year. As you can see, this night of activity for Perseid observations was very productive, and we totally have registered more than 800 Perseids. You can see plots ecliptic coordinates, radians of captured Perseids. So as a conclusion, last year we started operation 2 observation points in Tajikistan in the frame of global media network, and we hope that our joint collaboration will be very useful and productive. And finally, I would like to express our deep gratitude to GMN management, and especially to Dr. Denis Vida for providing video cameras and opportunity to be included in Global Meteor Network. Thank you very much for your attention.
Thank you so much. Tajikistan is uniquely positioned at a set of longitudes that almost, no other cameras observe, and that's why it's so strategically important. And thank you for hosting the cameras. Okay.
Thank you very much. Okay.
So next up is Danila Milanov. Go ahead. We can see your screen.
Hello.
And we can hear you. You're good to go.
Hello. Yes, I'm Danilo Milanov. Thank you for giving me an opportunity to present the data of our scientific group. Our results relate to the age of the GMN meteor stream. The GMNs are a meteor stream that produces strong meteor showers in the first half of December. Not only in the night sky, but also in scientific literature, the GMNs stand out as one of the most prominent meteor showers, having been the subject of numerous studies. However, the main mystery surrounding the GMNs remains unsolved. Their origin is unclear. According to widely accepted view, meteor showers consist of material from comets, which they shed while passing near the sun. The leading candidate for the Gemini's parent body is the asteroid Phaethon, discovered in 1983. Its orbit is very close to that of Gemini's meteoroids. However, aside from its elongated orbit, Phaethon does not resemble a comet in any way. This 6-kilometer wide rocky body approaches the Sun at a record close distance half that of Mercury. If it was ever covered in ice, it must have been a long time ago. Modeling suggests that asteroid's orbital shape has changed a little over the past 20,000 years. At the same time, most of estimates of the Gemini's age are significantly lower. Our study is based on analysis of the evolution of statistical characteristics of the sample of meteoroid orbits. Of course, we are talking about those meteoroids that have encountered our planet on their way, ceased to exist, but left a trace in our databases. To be more precise, we used orbital elements of 53,000 meteor orbits collected in the Global Meteor Network database over 5 years and identified with the Gemini stream. We traced the orbit of each of those meteoroids back 20,000 years using numerical integration. At each moment in time, we calculated the mean orbit of the resultant sample. You can see dependence of its elements of the mean orbit on time on the graphs. The x-axis shows time in millennia, and 0 corresponds to the current moment. A significant variation in inclination is noticeable, ranging from 13 to 45 degrees, while the eccentricity changes within the range of 0.81 to 0.93. The semi-major axis undergoes changes of no more than 0.05 astronomical units until approximately 15,000 years, after which this parameter sharply increases. The argument of pericenter longitude of the ascending node changes more significantly than other elements, completing almost a full revolution over the simulated time span. Let us step back here and think about the question, what is the mean orbit and how exactly to calculate its elements? We propose the following approach here. For a family of orbits, we will call the mean orbit the one that provides the global minimum to the square deviation of the sample. The set of points of global minimum of a deviation function is known as the Frechet mean. This type of mean represents a deeply meaningful generalization of the arithmetic mean to an abstract metric space. The root mean square deviation S in turn represents a natural generalization of the sample variance, describing the characteristic size of a random sample. This quantity plays an important role in our study, and henceforth we'll call it the dispersion. So to calculate the mean orbit and the dispersion, we need some distance function for orbits, distance between orbits. There are quite a lot of distance functions, usually called orbital similarity criteria. In our work, we use two metrics introduced by Konstantin Kholshernikov at the beginning of this century. The remarkable property is that the values do not depend on the choice of the system of orbital elements. Instead, they are determined by the vector integrals of motion in the two-body problem, the angular momentum and the eccentricity vector. The metric ρ2 gives the distance between orbits without taking into account the position of bodies on the orbit. The metric ρ5 is even less selective. It ignores differences in argument of pericenter and longitude of the ascending node of orbits. Here are the exact formula for calculating the parameters of the mean orbit and dispersion of the sample of orbits. The formulas given give the parameters of the mean orbit with respect to metric ρ2. The formulas for the mean relative to metric ρ5 are a little more cumbersome, but they still exist and can be found in our article. Now let's get back to Geminids. For each moment in time, we calculated the average orbit of our sample and its dispersion. The graphs on the slide are the dependence. On the slide, you see the graphs of the dependence of dispersion on time, on different time scale. As in the one-dimensional case, the purpose of our dispersion is to describe the characteristic size of the sample. We assume that for the ensemble of meteoroid orbits, this size was minimal at the time of the stream formation. In other words, the age of the stream should be sought among minima of the dependencies of S2 and S5 on time. The minimum of S5 occurs at the 1600 year mark. At this time, the orbits of the simulated stream were most densely concentrated around the mean in the ρ5 metric. Alongside the meteoroid orbits, the orbit of Phaethon, the presumed parent body of the stream, was modeled over the same time span. On the slide, you can see plots of the distance ρ2 and ρ5 between the mean stream orbit and the asteroid's orbit. The global minima of the average dependencies are located at 1,700 years for ρ2 and 1,200 years for ρ5. Thus, according to the modeling results, during the interval from 1,200 to 1,700 years ago, the considered sample of orbits had the smallest size in terms of root mean square deviation in S5, and its mean orbit was closest to the orbit of the presumed parent body. Assuming the Geminids are the result of the gas and dust outburst from Phaethon occurring near the perihelion of the asteroid's orbit, we can estimate the dispersion from above with the maximum distance ρ2 between Phaethon's orbit and the ejected particle's orbit. The slide shows the color graphs of maximum possible values of ρ2 for a fixed particle ejection velocity modulus. These curves are designated by letter R2 with the corresponding velocity indicated. The black line is the actual values of the S2 dispersion. Obviously, the black line must be below its upper estimate at the moment of the stream formation. This reasoning allows us to relate the particle ejection velocity to the age of the stream. The range of admissible values of this pair of quantities is shown in gray on the right. The graphs presented in previous slide were obtained on a sample of orbits in 2020. For samples of other years, the results look very similar. The quantitative differences in the estimates are reflected in the table. Here, tau and t are age estimates based on the minimum of S5 and the distance to the Phaethon orbit. The mean and V1600 are the lower estimates of the gas outflow velocity for ages of 0 and 1,600 years. It is clear that the estimates for different years are close to each other. Summarizing, we conclude that the age of Geminid is in the range from 1,200 to 2,000 years, which is included in the abstract of our article, the link to which is at the bottom of slide. If desired, our study can be reproduced and continued. We have made the calculated orbital elements for the entire simulation period and the integrated code publicly available. Thank you for your attention, and any questions are welcome.
Thank you so much for your talk, for determining the age or estimating the age of the Geminids using this novel method. That was great. So officially we are into our break time, but I'd be happy to take some time from the break, or who wants to walk away, go ahead. But if you have any questions, feel free to ask. And also, if you have any questions about any other previous talks, you can also write them in the chat, and then the speakers, please look there as well. So Paul has a question. Paul, go ahead.
This is for the last speaker. Thank you for that very interesting talk about the Geminids. I'm wondering if you had a chance to compare your orbital results with, for example, the right ascension and declination of the Geminid radiants or any of the other Geminid meteor shower known parameters. Have you been able to do this yet, or is that for future work maybe?
Maybe, but actually we didn't simulate the meteoroid stream itself. Instead, we took existing orbits, which elements we found in the global meteor network, and traced them back to the past. So we didn't make any synthetic particles.
Mhm.
Everything is real.
Okay, thank you.
You're welcome.
Any other questions for any of the speakers? Well, if not, thank you, Danila. And we'll see everyone back in about 2 minutes. We're going to start, Elizabeth is going to start off at the full hour. And that's it. Okay, thank you. Okay, Elizabeth, maybe you can share your screen and get the slides ready, and then we can start exactly on time.
Can you see my screen?
Yes,
Or
I
my
can.
slides? Okay, that's wonderful. Thank you.
We could hear you and everything's great. So,
Okay, perfect.
and I think you can start. We are right on time.
Okay, fantastic. Thank you. So first, I would like to thank my co-authors and numerous people of the GMN for wonderful all-sky camera observations of this fireball. And when publication comes out, we'll make sure that we acknowledge everyone here. So I'll just start with a little bit of a background since we have different sensing modality when it comes to this specific fireball. We are interested in characterizing fireballs and bolides through different means of observations. Of course, optical observations are the most meaningful because we can gather a lot of information, but the idea is that we can also use infrasound, which is very low frequency sound below human hearing range, that can propagate over very long distances and carry signatures of the shock wave generated by a fireball. And additional idea behind it is if we have any sort of fragmentation event, or if there is an airburst, that infrasound signature may carry some information about that. So as I mentioned, all-sky camera observations are extremely meaningful and extremely useful because we can gather very accurate information about the trajectory, entry speed, and other parameters. I'm not going to go into those details because we have quite a group here that is specializing on this particular topic. However, meteoroids, as they propagate through the atmosphere, because of their speed and combination of their size, they can generate a shock wave. And this shock wave, as it propagates outward, decays to low frequency acoustic wave that can be detected over very long distances. We're talking about hundreds and even thousands of kilometers, depending on the size and energy of that particular event. Here I will be talking about earth grazers. Earth grazers are extremely rare just because they belong to that very narrow Gaussian distribution tail of all of the impacts. These are unique because they enter the Earth's atmosphere at extremely shallow angle and just skip back into space unless they lose enough energy and fall down to the ground. There is only a handful of such events detected by all sky cameras. And in fact, only one was confirmed to be detected by infrasound. That was 1972 gray daylight fireball, which occurred over North America. And it was, as I mentioned, detected via infrasound as well. But at the time, records were classified and they have been lost since. So we basically don't have any confirmed infrasonic observations of earth grazers. In 2020, on September 22nd, there was an earth grazer that entered over Northern Europe at 03:53:40 UTC. It was seen by many eyewitnesses as well as observed by numerous ground-based cameras. It just happened to pass over the Netherlands as well, and there we have infrasound network that had 3 stations operational at the time. So as per the analysis of global meteor network, the luminous path was pretty much horizon to horizon. It started over Germany, ended over the UK, and the altitude was fairly high. So it entered at 101 kilometers, exited at 107, but it never really went below 90 kilometers. For comparison, the Great Daylight Fireball from 1972, the lowest altitude was about either 45 or 49 kilometers. So it was much more deeper penetrating fireball. So the point of closest approach for this one was 90 kilometers. It was very high velocity, 34 kilometers per second. And of course, as it lost energy, it exited at slightly lower velocities. So here is the ground track. The propagation here is from northeast to southwest, and annotated are the three stations of the Netherlands infrasound network, EXL, DBN, CIA. EXL is very close, actually almost nearly vertical relative to the fireball trajectory. So even though it was very high altitude and apparently silent to humans, the fireball was detected by infrasound sensors. It produced quite a strong signal, as a matter of fact. The signal was first detected at TXL. This is the closest station, 4 seconds after the entry, and for a few minutes after the entry, because it takes for infrasound wave to travel at sound speed down to the station. And all signatures at all three stations exhibited a so-called N-wave appearance, which is diagnostic of a ballistic shock, which means it basically traveled perpendicularly outward from the trajectory. That also indicates that we had cylindrical line source or no fragmentation during the passage, which was, of course, confirmed by all sky cameras. The signal trace velocity, or the speed and angle at which air wave arrives at the station, was very steep, which indicates almost a direct arrival from high altitude shock produced by the cylindrical line source. So signals were received at all three stations and were associated with these ballistic arrivals. And here's the example of one of the stations. This is the TXL array, which is the closest one. In the upper left, we see N-wave signature. So it was very prominent signature. And then in the other plots, we see in the panel B, FSTAT, basically, which provides correlation to the signal. Back azimuth is panel C, which indicates the direction from which air wave arrives at the station. And D is trace velocity, which indicates and gives us information how steep is the signal coming down to the array. Usually trace velocities are slightly higher than speed of sound, but in this case, it's extremely high, which indicates very steep arrival. And we rarely see arrivals this steep. We only see them if we have geometry, such as here, where something is very high altitude and then it arrives almost vertically at the station. Here is the spectrogram. So the frequency content was mostly below 4 Hertz. And the average dominant signal period, so we measured the signal period and amplitude at all stations, was 1.2 seconds. And this indicates approximately 7 to 10 tons of TNT equivalent energy release. So where optical observations are really important and came into place, and I really thank my co-authors and everyone else who has contributed with video observations, is that we have very accurate trajectory, and with this accurate trajectory and information about the whereabouts of the fireball, we can then perform additional propagation modeling. We can also do weak shock modeling to derive certain information about the properties of how the shock wave was generated, as well as try to determine the source function, specifically to determine where exactly the shock wave came from, and also if we can link it to the size and mass of the meteoroid. So we performed propagation modeling using trajectory derived through all sky camera observations, and we've been able to pinpoint exactly where the signal came from. And as a matter of fact, which was very interesting, we have determined that each station captured a different portion of the trail. And in the plot, I show the back azimuth versus travel time. So by correlating these two quantities, we can actually determine where exactly the signal came from. And we have found that shock source altitude in each case was just above 91 kilometers, which is very high for infrasound to be captured from such heights. We also performed weak shock modeling. I'm not going to go into a whole lot of detail here. Nevertheless, I just want to, for the sake of time, I want to mention that we have been able to determine meteoroid mass of about 28 kilograms and a size of 25 centimeters, which is consistent with what was derived through all sky camera observations. So if anyone wants to discuss this further, I'm happy to share my slides. And also you have my email. It's on the first slide as well as the last slide. So feel free to reach out to me. Nevertheless, I just want to mention in conclusion that we have been able to capture infrasound signals from very high altitude, which is rare. This is mostly attributed to the very rapid ablation, which has shifted the Knudsen number of the fireball and enabled the formation of the shockwave. And this is the first time we have confirmed signals from different parts of the trail at different stations. And that's all for me for now.
Thank you. We have time for one quick question. Does anyone have a question for Elizabeth? Go ahead.
Hi, Elizabeth.
Hi.
Thanks for a really good talk and nice to chat with you again. Sorry, I may have missed it. It sounds like this was very well measured, but um, if I missed this, was the orbit of the incoming fireball measured sufficiently accurately to say something about where it might have come from?
That's actually an excellent question, and thank you for asking that. I skimmed over that because no time, but yes, Dennis, in fact, and Tammy and Jamie worked on obtaining accurate trajectory as well as orbital parameters. So I think Dennis can comment a little bit more on that, where exactly it comes from. But yes, we've been able actually to pinpoint the origin of it.
Yeah, we have a really good orbit, and Tammy ran numerical integration, so we have also a good idea of the associated uncertainties. So, yeah, back and forth.
Excellent. And can I ask just another quick question while I'm on here? So, um, you mentioned that it was silent to humans, but is
Yes.
there any way of estimating how, like, was it expected to be audible? Like, can you estimate how loud it should have been? Is that surprising that it wasn't heard, or because it's so high, it's really just not expected to be heard at all?
So in this case, it's not really expected, but as with any meteors, especially when people are close to the trajectory, we do have evidence of meteoroids producing sonic booms. There was actually a recent fireball over New Jersey, and it produced very audible sonic booms, as well as in other situations. And initially, when you see a fireball, it's very difficult unless you have all sky camera observations and do some analysis to determine what the exact altitude is of the object. So I can't really say whether we would expect something from such a high altitude. Probably not, because only lower frequencies will survive, and everything higher frequency would get easily absorbed. But it's not unheard of fireballs to produce sonic booms, audible sonic booms at the ground.
Okay.
Elizabeth, if anyone else has any questions, please put them in the chat. And next up, we have Dario. Dario, go ahead.
Hello.
We can see the screen, we can see you, and we can hear you. You're good to go.
Great. So in this talk, I'll go briefly over the software architecture of RMS, which, as you know, is running on all of the stations of the global meteor network. So from the very start, we knew software needs to be written in a way which makes it both easy to maintain and easy to validate. So Python seemed like a good choice. But at the same time, it had to be performant enough to run on Raspberry Pi. So some critical path routines, you will see that they're written in Cython, or they're calling to one library we have in C++. And yeah, if you'd like to check the software, it's all available on GitHub. So one way we can approach software architecture is to see how the data flows in RMS. So in our case, our goal is to go from video observation all the way to orbit. And in that process, we have to go through distinct set of steps. We're not really interested in this talk, how any specific step is done, which methods are used, or algorithmic details. We're just interested in how all of it is glued together. So in that video data, in one way or another, reaches to the first Python routine in RMS, which is buffered capture. On most Raspberry Pi stations nowadays, I imagine that goes through GStreamer, which does GPU decoding of H.264 data that's streamed by RTSP from the video camera. And then buffer capture has a really simple job of just putting those video frames into a shared memory in a blocks of 256 frames, and that block will be further processed. Once the one block is fully filled, buffer capture switches to the another block while that first block is being processed. As well, with some recent additions to RMS, buffer capture will make sure that that data also gets dumped to separate files. First part of that real-time processing is compression, which produces FTP for temporal pixels format of encoding video data. So that gets saved to FFFITS files, but it also gets is still preserved in memory, so it can be used by video extractor. Both of these steps, compression and video extractor, need to run while those 256 frames in memory are not overwritten by the next step, by the next sequence of video frames. So they have a short time to execute. Back in Raspberry Pi 2 days, that was a bit hard to fit all of the processing in that real time. Nowadays, it's not so much of an issue. But yeah, from real-time processing, we get fireball files and FTP files and field sums. And also compression, once it has the file ready, it marks that file as ready for detection. That goes through indirection layer of queued pool, which is basically just a pool of things we need to process. In this case, list of FTP files. During the detection loop, which is either called by compression, like we saw before, or on reprocessing, on final processing of the night. Those FTP files have to be loaded because they're no longer in memory, and then we extract stars and we detect meteors, all of which are described in a lot of detail in papers that have been published, but for the interest of this talk, we are just interested in what they output, which is the calibration and detection files. Also, those same routines are called on reprocessing of the night when we are interested in recalibrating all of the data, in which case calibration files are read back and new ones are written with the continuous recalibration of the plate parameters. If we are interested in viewing the software more from a system level than how the data flows, there is no better place to look than Start Capture module, which is kind of the manager of the whole RMS. So when the camera starts, OS calls RMS Start Capture shell script with some parameters, which call Start Capture module, which initializes basically everything that RMS does automatically. So it initializes buffer capture, creates those 2 blocks of shared memory, initializes compression, initializes detection queue, and all of that is running during the night cycle. But when the night is over, buffer capture and compression are stopped, and we can allocate more CPU cores to the detection, at which case we are just processing FTP files. Once that's done, we can reprocess the whole night and calibrate, do a calibration step we previously mentioned, and then a whole batch of a night is uploaded. As well, Start Capture, when it starts, checks if any old data has not been processed and need to be reprocessed, or if, for example, Event Manager is telling it to upload any specific files. But yeah, basically, if you're interested in exploring RMS, start with the Start Capture, and from there, you can find almost anything. All of the modules that we talked about are in the RMS folder, which is, it holds all of the main modules, and then those modules call to specific routines in the routines folder, or they call to wrappers around the various different formats that RMS uses in formats folder, or we have a folder for astrometric routines. Likewise, there's a utility folder, utils, which holds a lot of different scripts that are not usually called, well, most of them are not called automatically during the processing during the night or during the day, but they're available to be called manually for specific steps that an operator might need to do. Most notably of those, there is a SkyFit 2. If you're interested in how that works, you can check Dennis's talk from last year. But yeah, there's a whole host of utilities there from for checking the live stream, or for viewing different files, or to do a single station reductions and similar. One of the main dependencies in RMS is NumPy, which was really crucial to get that runtime performance in Python, as well as those Cython routines. And there's a lot of dependencies, but quite manageable list, I would say. And of course, we mentioned that our goal is to go from a video station, from a video observation all the way to orbit. We are not there yet. We are with RMS. We just have a single station observation, and it has been uploaded to a server. But from there, we need orbit estimation, which is done by a separate set of software. You can check Western Meteor Python library, which holds trajectory solver and a bunch of other useful packages for meteor science, as well as there are other related open source projects that have sprawled around global meteor network. Thank you. Are there any questions?
Thank you, Dario. Any questions for Dario? This talk was he created by popular demand. People wanted to know how the software works in different modules. And just for everyone's context, in case you don't know, Dario actually was the initiator of the RMS software and wrote the first version almost 10 years ago now. So, go ahead.
Hello, Dario. Thank you for the interesting presentation. Do you have any results about the precision and recall of this software in terms of meters identification and maybe the orbit extraction? How well it does its work? Maybe some quality metrics.
I think this would be a better question for Dennis.
Yeah, it really depends on the detection settings that you use. Have we ever evaluated it manually? I mean, we have. We did look through some manual videos, and you can actually check yourself by comparing what's called the captured stack versus the detected stack. And if you see some meteors are missing, then that detector didn't pick it up. And every once in a while, I get a similar question, and I go in and I look through the data, and then either the meteor was too short or it was actually a satellite. It was too slow. It wasn't a meteor. So I would say at least 90%, maybe more. I don't have any hard numbers, but it also depends on the camera. So if you use a different kind of camera, it might need some different kind of detection settings. But it's pretty much picking up almost everything that it's supposed to pick up above the noise level. That's fast enough and has at least 4 well-observed points above the thresholds.
Okay, thank you.
Thank you. Okay, and I think our next speaker is ready to talk. So Damir, go ahead. Feel free
Yes,
to share.
just a second to pick the right screen to share. Should be on your screens now, yes?
We can see the screen, we can hear you, and we can see you. So go ahead.
Okay, so I will start explanation how we can actually measure brightness of stars which are fixed, which don't change, and consequently variable stars to compare with them. What's the driver is the fact that we have lots of questions. Is it possible to actually estimate the brightness of variable stars? T Corona Borealis is the driver lately, waiting for explode. We are waiting it to be seen on the pearl in Corona Borealis. But here in this presentation, we will explain how to accurately measure stellar magnitudes from data we already have in calstars.txt files. As a case study, we picked Delta Cephei. What will be done there? It will be some kind of differential photometry, and we will do a comparison with EVSO data, so to see what is about precision of our observations. So, as you know, we produce extremely big number of data on nightly basis, daily, nightly, whatever. During the night, we collect information for plenty of stars. If we look overall, we speak about hundreds of thousands and even over a million star measurements for each night. Nights from the extreme north or south parts of the globe during winter nights of theirs, they usually pick more than a million stars during the night. So actually, we don't see million of stars on the images, but we are able to measure multiple brightness values for stars going through the field of view. Those brightness of the stars is not currently tracked, so we don't have the information about their magnitude, and we can see only from results coming out from the photometry solutions that some photometric errors are between 0.1 and 0.3 magnitudes. How can we actually measure stellar magnitudes we don't have this part embedded in our pipeline, but we can do some kind of cheating here. So we can pick all stars listed in CalStars. Then we can create a fake plate part detected info, like those stars were actually detections of meteors. And then we can recalibrate and apply astrometry on that fake FTP detected info file, which will result in stars positions and their magnitude. Now, what is important to do is to see here is that we should only in config file set the interless order to -2, because this means that those observations will kind of be taken with the camera with the global shutter. So we will have XY values and consequently right extension and declination not affected by rolling shutter effect. And next point is just to extract stars and match them with the catalog ones. I took precision of 12, okay, 0.05 degrees, which turns out to be close enough. Picked delta Cepheid for that purpose, and you don't have to be a variable star observer to understand that you should pick reference stars as close as possible to the variable star you would like to observe. So in this case, I picked zeta and epsilon Cepheid. There is a trick here. Actually, unfortunately, both zeta and epsilon are variable stars themselves. Luckily enough, their amplitude of variation is too small to be detected with our 8-bit video compressed heavily. So those should do. At least we will check out how good will it do. To see how good we do on stars that don't significantly change their magnitude, I picked up Zeta Cepheid as first and check it out through various nights, how much the variation of measured brightness in magnitudes. And it turns out that we have like 0.1 magnitude as one standard deviation of error. You can see that at some points we have some strange values coming out during some either clouds being present or something else obstructed, like contrast, the light coming in from the star. So, okay, that's Zeta Cepheid, which is 2.6 magnitudes bright. If we go and look at Epsilon Cepheid, which is 3.8 magnitudes bright, we can see that the standard deviation of the data set varies up to 0.14 magnitudes. It is not so promising. And when we look at Zeta as alone compared to reference epsilon, reference star 2, and then we compute the difference between those two, we can see that still the standard deviation of difference is a bit higher, naturally, of 0.15 magnitudes. However, if we run some average on 10 minutes chunks, so we take 10 minutes of FF files of ours, it means we will have 60 observation of the same star there, and then calculate standard magnitude of those data sets. It turns out that the standard deviation is about 0.06 magnitudes. Those two stars vary a bit, so perhaps there is something of variations embedded here in that standard deviation. And now we are ready to check it out, what will happen if we start comparing results from other stations, not from a single station. So First, we had only station HR 0024. Now, if we see what it looked like for reference star theta Cepheid from camera 1Z, creation camera 1Z, you see that variations are much, much higher. If you look at USA 1J camera, it is similar to that, but take a look on how much is the difference between those magnitudes. It is magnitude variation we would see if we would actually measure meteor. It is not something that is we want to see, and something that should be tackled somewhere in the future. And then if we add delta Cepheid here measurements, you can see that it's not so promising at all. Going back, however, to one single station observation, we can see that those look pretty consistent. So here you have multiple data from multiple nights processed, covering the whole period of delta Cepheid variable star changes, and you can see it is looks promising. Please note here how those rough and very raw observations during nighttime, during cloudy nights and stuff like that, got suppressed when you use differential photometry. And now it looks much more consistent compared to raw data set from above. And if you look at what it will be looking like compared to results I downloaded from American Association of Variable Star Observers, well, it doesn't look too bad. I'd said it look very promising. So if you look better at it, you can see that deviations from ABSO data are pretty much always inside 1 sigma from measurements coming in from GMN data. And if we look, what would it look like if we combine data from multiple stations, you can see that some stations show some perhaps something like a variation which can be suppressed. Those differences may be coming in from different camera types, sensor types, or even glass in front of the camera, so shield glass, which may be of different transmission in sense of spectral transmission, and that may be the reason for those deviations. You should know that delta Cepheid has different amplitude when you're looking at different spectral bands. So this is not something that is not expected, and we should just check it out how it we may correct for that. But if you have plenty of data and run it through all of the year, or like in this case 3 years, you end out with more than 200,000 observations from a single station, and then a light curve from delta Cepheid would look like this. To conclude, differential photometry is really helping us out here. There are some errors introduced, most probably by slow-moving clouds, or changing the offset of camera. You should know that here no corrections were done, neither for extinction, neither for except from flap fielding, which is not a real one, but only vignetting. So not all camera will be synchronized, so to say. But comparison with the AVSO data may help to pick out the ones which are in good agreement with those, and then we can use them in some automated process of monitoring of variable stars. There are most certainly other better ways of to do this kind of analysis. Whoever is interested in, please go ahead. Some possible improvements would be to have some better vignetting, flat or extinction corrections to start with, or to apply some different kind of averaging, signal averaging or stuff like that. So pretty much I hope I did it in time. Thank you very much.
Good. Thank you, Damir. We are a bit short on time, so I would like to transition to the second talk, but I can see this generating a lot of attention and questions, so feel free to either put them in the chat or we're going to have a pretty long break after this last talk. And then there are going to be some breakout rooms and you can chat there. So Jamie, feel free to share your screen and start your talk.
Okay, everyone hear me okay?
It's looking good. You can go ahead.
I'm going to talk to you about things that cause curvature in meteor trajectories and also look at ways we can correct for that. Now, this lovely fireball came right over my house last October. It was seen by several cameras of the Global Meteor Network. Okay, it was changing before. Let me get the slides to change. Okay, it's frozen up. There we go. Seen by several cameras of the Global Meteor Network. And in the analysis, we can see that there's an obvious deviation at the end of the trail. Now, what's causing that? First of all, it could be observational error. Here's one that flew over England last month. And if we look at the raw observations, we plot them on the graph, and there's quite a lot of wild errors where the residual errors go above and below the line. Now, if we look at the stack of all those observations, one thing I find is that if meteors venture into the edges and corners of the field, that's where these measurement errors pile up. So we can get rid of those just by chopping off the data from the files and reanalyze. And on the right there, you can see that the fit is a lot better. But that doesn't really explain our observation here. It's right in the center of the frame, this gray track at the right there. And so we're looking for an explanation possibly to do with wind effects in the upper atmosphere. Now, it gets pretty windy up in the upper stratosphere at the latitude of the United Kingdom. You have this thing called the polar night jet, and the winds can reach speeds of 50 meters per second and on up. So that seems to be there's a lot of wind that we need to look at. It's the polar vortex, and there it is blowing right over the UK. And so what we did was we used a method of correction which was very similar to the one used for gravity correction. That's already built into the solver, and that's a vertical vector that we subtract. So with wind correction, we can do the same thing with a horizontal vector. We programmed it up, and I started off with that polar night jet velocity, 50 meters per second. And we can see that it doesn't do very much with the correction at all. But having gone to all that trouble of making the software do what I wanted, I decided just, what the hell, I'll keep going. So we doubled it up to 100 meters per second. Things are getting a little bit better, not much. Double again, 200 meters per second, and things are starting to look good. So add another 100 meters per second, and the fit is pretty good at the end of the trajectory now. But that leaves us with a problem. The polar vortex can only reach 70 odd meters per second on a bad day. It's simply not fast enough to explain the effect. So I was feeling pretty dejected at this point, gone up a blind alley, but then an idea struck me. There actually is something that is fast enough, and that's a frame of reference. Now, we do all our fireball calculations in the Earth-centered inertial frame of reference. That's the green arrows there. The axes point towards the fixed stars, and the Earth is rotating relative to that. So when a fireball enters the atmosphere in that frame of reference, it's experiencing a side wind of the Earth's rotation speed as well as the polar vortex. You add the two together, vector addition, you come out at almost exactly 300 meters per second up here in the UK. Now let's look at a real example of that. Here's a fireball that was probably dropped a small meteorite. Happened over Staffordshire last May, and searches were carried out, but nothing was found. Now here's doing the analysis without any of this wind correction. Look carefully at the points at the bottom of that right-hand graph where the fireball penetrates to nearly 20 kilometers height. Once we apply the wind correction, we get a very much improved fit. Now the fireball came in very steeply, so we'd expect the strewn field to be not far past the luminous end of flight. And if we look right down at the ground at projecting the path of the fireball onto the fields, we can see that the wind-corrected version is off to the east of the uncorrected version. And one thing that is noticeable is that the plot of all the points along the trajectory is pretty straight, whereas if we don't do the correction, we get a curve. Now, this makes sense if you think that if you were standing there watching the fireball, on the Earth, the air the fireball's passing through is going at the same speed as you. So the fireball would slow down without being shifted sideways. Yet if you do the correction in the inertial frame relative to outer space, then there's a strong sideways wind, and that's what creates the curvature. And if the correction also affects when you project past the end point onwards, because the azimuth of the travel has changed. Uncorrected on the left there, corrected on the right. And the difference I found was about 3 degrees. Remember, you're looking at this thing vertically, so the deviation is exaggerated because you're almost looking at it edge on. But if we superimpose that on the calculated strewn field, the orange boxes were where people spent a couple of days searching for meteorites. And we can see that the amount of deflection applying the correction is very comparable to the width of the search boxes. So this is something we really need to look at in relation to meteorite strewn fields. So I'll leave that one there. The next thing I want to look at is refraction parallax. Now, the only paper I could find about it was this one. And what this team did was they looked at ray tracing of parallax relative to a formula. Just to explain a little about parallax, meteors don't happen at infinity, and refraction bends the light through the atmosphere. So you're going to see the meteor against the sky as if you were standing in a position above where the observing station actually is. Now, comparing the formula with ray tracing, the gold standard of refraction calculation, they only calculated it up to 20 degrees. That's the red spots there. We can see that the green formula is pretty good at low elevations, but at high elevations, it's actually worse than no correction at all. So that's not much good for us. I wanted to find a formula we could use in the solver, and we can approximate the atmosphere to a flat slab of air at the same density as the surface, and we get a slab of air at 8.4 kilometers thick. And the refraction can be considered to all happen at the top surface of that layer. And so the flat Earth formula is derived at the bottom there, delta Z for the change in height that you have to apply. And when we apply that formula, we get the green squares. Pretty good correction above 20 degrees, and it also tracks the ray tracing pretty well as well, and only breaks down if you're only a few degrees above the horizon. But once having done that, you can actually bend that slab of atmosphere around the curvature of the Earth. And what I did was I took the same refraction, but used the increased angle of incidence of the light ray at the top of the slab of air. And it increases by that angle alpha, which you can calculate with this equation. And we end up with a revised formula for the delta Z, which looks very like the flat Earth one, but just with an increased angle of incidence. And if we plot that one, we end up with the blue triangles, and that agrees nicely right down to 2 degrees, which is below where any useful fireball observations are likely to be made. So here's an example of that. None of these stations were particularly near the fireball, which came quite low, and plotting those without the parallax, there's quite an error at the end of the flight. It lasted 9 seconds. And if we apply the parallax correction, everything fits a lot better, especially at the end of the trajectory. Now, where does that leave us? Well, if you're doing meteor observations, as long as you're looking high in the sky above 20 degrees, and as long as the meteors don't come below about 50 kilometers height, neither of these corrections are really applicable or necessary. But for meteorite hunting, it's a different story. It's the one that really makes the difference is that correction needed for the atmosphere moving at the speed of the Earth's rotation in Earth-centered inertial coordinates. If you don't do that, your strewn fields are going to be out. The examples I tested, 200, 300, perhaps 400 meters, depending on the geometry of the fireball. And that's it. Thank you for listening.
Wow, amazing job, Jamie. I mean, that's these are some things that we started exploring, and the coordinate system issue is something that pops up every once in a while. The original intent of the solver that we developed in the Earth-centered inertial system was mostly for fainter meteors, and you're right to point out when you use this solver for fireballs that penetrated deeply, then it makes more sense to use the Earth-centered, Earth-fixed coordinate system where you don't have these particular issues. But if we can implement these corrections to WMPL so both work, that would be amazing. Yeah. Are there any quick questions for Jamie? I'm going to allow for a couple of minutes, and then we're going to have a long break during which more discussions can happen.
The thing I didn't mention is that we use the lag curve as a way of working out the wind correction. The fireball is slowing down in the atmosphere, and the lag curve gives you a direct measurement of how much it's slowed down. So if it's slowing down in a moving air mass, such as the rotating Earth air, then it's just a simple multiplication. You divide the wind speed by the meteor entry velocity and multiply that by the lag, and that gives you the amount of the correction.
Makes perfect sense. Okay, well, if there are no questions for Jamie, we are going to begin our break, which is going to last until 25 minutes after the full hour, so which is in about 32 minutes or so. I will leave the meeting running, and I will create some breakout rooms. So if you'd like to talk to some of the speakers about their work, and in case they're not gonna eat a meal or something, feel free to do so, and then see everyone back in about 35 minutes. So thank you. Okay, breakout rooms are created. Feel free to go there and contact any of the people you want to chat with, or just put your question in the chat. Thank you. See everyone in 30 minutes.
All right. All right. I'm hoping all of you can see that pretty clear.
We can see it and we can hear you. Go ahead.
All right, yeah, thanks all of you for talking. Thanks very much for the invite. I'm going to be talking about a rock that fell apart over the Great Lakes 2022 WJ1 today. And there's a lot of ground to cover, so I'll just say immediately, you can just go read our paper, which was published at the end of last year. A bunch of our co-authors are here on the call today. And, you know, like with any paper that tries to do something new, it really was a really big group effort. And I think we're all really excited about some of the results that we got out of this. Let me start my timer so I don't go way over. So in particular, it's kind of hard to study, you know, meteoroids with multiple different techniques because telescopes are good at finding big things far away. Meteor cameras find them up close. And if you want to actually see these techniques cross over, it requires some luck and preparation, right? The object needs to be found far enough in advance that telescopes can point at it, and then it needs to land in an area or near an area with significant meteor camera coverage. As a result, these kinds of techniques haven't been able to be applied to the same object before. You know, one of the big reasons that you might want to do this is we want to understand the whole process from asteroid out in space to meteoroid to meteor to meteorite on the ground, right? You can see a picture of the asteroid 2008 TC3 after it is burned up and landed on the ground here in the desert. And this is sort of the way that, you know, the field existed at the time that we were doing this project, right? We have linked telescopic data to meteorites on the ground. We have linked fireball data to meteorites on the ground, but telescope to fireball linkages have been challenging. And we want to understand, do you draw the same kinds of conclusions about, you know, the same objects getting studied with different techniques, right? Do they tell the same story? So 2022 WJ1, you can see the discovery images on the right here from the Catalina Sky Survey, was discovered a couple of hours before it impacted the Earth. Within a couple of minutes, we knew that it had a better 50% chance of impact, and within an hour, it had reached 100% very, very firmly, with the impact predicted around 827 UTC. The last astrometric position, so the last time a telescope reported the position of this object with respect to the background stars, was at 7:59 UTC, so about 28 minutes prior to impact by myself and colleagues. The reason that we could not push it further, despite the object, you know, is still getting closer to the Earth, right? Should have been getting brighter, is that it moved into the shadow of the Earth. And as a result, we weren't seeing any reflected light from this rock anymore. Here's a video of 2022 WJ1, this asteroid that we observed with the telescope burning up behind the CN tower. And you can see the fragments right there. The sort of goal we had for this project was to ask, do we tell the same story if we compare telescopic data taken with the Lowell Discovery Telescope, Lowell's big 4.3 meter? You can see a picture of me back when I used to have a full beard with some of my students back there. To the kinds of data you get from the cameras that we've been talking about today and we'll be talking about tomorrow a little bit as well. This is the first time that we've had this opportunity to ask how well these kinds of techniques compare. Do we infer the same size for the object, the same composition, the same strength? Let me walk you a little bit through how the telescopic data acquisition went. This was challenging. At the time, the Lowell Discovery Telescope, we could only point it at named asteroids. This object did not get given a formal asteroidal designation until after it ceased to exist. This has since been rectified. We've worked with JPL a little bit. But it meant that we had to just point where the object would be and watch it move through the field of view. So you can see the streak on the left-hand side of the screen. That's the length over which 2022 WJ1 moved in a single exposure. We extracted the brightness of WJ1 along the streak. So sort of like you can imagine it's like a little slice of how bright it was over a few seconds. That becomes each of those little black squiggles on the right-hand side with the white the white dot in the middle being the actual average for each of those little streaks. So we didn't just do this in one filter, we did it in multiple. The Sloan GRIZ filter set, for those of you who use telescopic data, This isn't quite enough to be able to say, oh, this is exactly the kind of meteorite we would expect it to be. But with four filter and thus three color photometry, we can discriminate between a carbonaceous dark surface, like you'd expect from a carbonaceous asteroid or potentially a comet, or a rockier, brighter surface. We can also get some constraint on rotation state. I won't talk too much about the rotation state here today. We couldn't really figure out exactly what it was for this object, maybe because it was spherical or it was rotating too fast or too slow. But you can see that because we were able to get it in multiple filters, we can compare those brightnesses. And converting those brightnesses we measured to solar reflectance values, meaning we're comparing how bright it is at each of those wavelengths compared to the sun, and thus how well it's reflecting sunlight. This object appears rocky. It has a 1 micron absorption feature common for silicate-bearing asteroids, and that means high albedo, and thus a smaller size likely. When asteroid scientists say high albedo in this context, it means, let's say, like 15 to 20% and above. So still not extremely bright, but compared to the rocks that reflect only 2 or 3% of the light, they're quite a bit brighter. You'll see that when you compare the colors that we got, those white dots to, for instance, the asteroid taxonomies, so sort of ways that asteroids typically reflect light, the fits are okay. It's sort of hard to know exactly how bad a mismatch this might be with the errors we have on the data set. We can say it's silicate rich, but past that, it's a little bit tough. We compared it with meteorites again on the right, not the best fits in the world. One reason we think this might be, potentially, is that this object just doesn't have a lot of dust or what people say regolith on its surface, right? Large asteroids through micrometeorite bombardment will be covered in, powders and gravels and stuff. Those reflect light very differently than an exposed solid rock surface. So if this object didn't have a lot of regolith, and it is just pretty small, we think a couple meters and less, and I'll give you the real size in a minute, that might explain why its surface reflects light very differently than the larger asteroids we've studied more frequently. These are just 2 papers by students of mine who have done sort of work studying grain size dependencies in asteroids. So it's an interesting topic I'd be happy to talk about more. I feel like I don't really need to give this pitch, but one of the reasons this is a really interesting comparison to make is that telescopes can study only the outsides of these objects, right? We're looking at reflected light. That's why we lost it in the shadow of the Earth. How the object ablates and fragments on the way in is more sensitive to some of those properties that telescopes just can't measure, right? These are not things that we can detect correctly or detect exactly, but we can compare to meteorites. We have to use comparisons and approximations, but let's check. Sort of as a proof of concept here, the orbits derived from both telescopic and meteor camera datasets agreed within tens of meters, which is really, really great precision. You can see some of the datasets that I'm sure some of you were involved in on the right. Models that can reproduce the actual flaring and trajectory of the object. We can get really, really great fits to our data, and this means that we can start to really understand some of these physical properties that you derived for 2022 WJ1. You can see again the object fragmenting on the left. Those kinds of fragmentations are the spikes you're seeing in the light curve on the right. This means that we can ask, whether or not there was dust on its surface. Was there lots of regolith? We don't see evidence for early dust release. This is good, but maybe not the most perfectly conclusive evidence that there wasn't, dust on its surface, but it agrees with some of the colors we got. And the fragmentation, the dynamic pressures at which fragmentation occurred are pretty darn closely matched to the ordinary chondrites. Again, a stony, rocky kind of meteorite, well linked to these silicate-rich asteroids. In broad sense, both techniques have now said this is probably rocky, moderate to high albedo, dense, like the ordinary chondrites, maybe without much dust on its surface. So we can compare notes here. This means that, maybe we're telling the same story with the same techniques, and that means that we can ask some really interesting questions here. If both the colors and the actual light curve itself both suggest there wasn't a lot of regolith on its surface, that's a good sort of way to inspect the properties of these smallest asteroids that are so hard to study otherwise. And people had predicted, smaller the asteroid gets, it should be harder and harder for these objects to hold on to regolith. This is a good sign. Both techniques agree on the broad size of the objects, between 40 and 60 centimeters. If you pick the middle number of 50 and compare it to the average size human, that's the diagram on the right. This is the smallest asteroid that's ever been characterized in space. I think that knowing what we know now, we could do so much better, even with the same amount of telescope time on sky. But I think this is a really important step forward in showing that not only these techniques are comparable and compatible, but they also give similar answers and allow you to say some things with a lot more certainty. You might ask, where are the rocks on the ground? The largest surviving chunk is probably in a vineyard. So this is my joke slide. But if you're interested in helping with this research, if you start testing wine from Canada for iridium content, maybe you can help us figure out which vineyard it is. I can keep buying Canadian wine, but this is mostly for my personal purposes and not for research purposes. So, but maybe all of you have some other ideas here too. So I showed you this plot earlier with lists of all these different impactors and their relative sizes. 2022 WJ1 is in the far left-hand side of this plot, half a meter in size. By combining telescopic and meteor camera data, we can say that it's half a meter in size. It has mechanical and reflective properties like the ordinary chondrite meteorites. It probably didn't have much regolith and was probably a relatively intact large boulder. I think that in the future, people are going to be blowing this kind of research out of the water as we find fireballs earlier with stuff like the Rubin Observatory's LSST, and as meteor camera networks expand. It could very well be that we've done the best we could here, but 3 or 4 years down the line, some graduate student is going to be, understanding these objects at a much greater detail and be able to ask much more in-depth questions. And I think it's a really exciting time. So if any of you have any questions or suggestions for future work, my email's on the slide, and I'll say thanks so much.
Amazing talk, Teddy. Any questions for Teddy? Okay, Paul, go ahead.
Hi, Teddy. Thanks for that really interesting talk. And you kind of alluded to it at the end, but I mean, what you did with the Lowell telescope was sort of Herculean. Like, it's amazing that you were able to get that data. But you did mention that if you had to do it all over again, you might do things differently. And I'm just curious what would you do this time if the exact same event happened again?
Sure. So I didn't mention this talk. We've since gotten another impactor and done better. We haven't finished processing the data, so I wasn't going to show it or anything. But one of the things we've realized better, just as we've been able to acquire these objects' orbits earlier, get quicker at getting on the telescope, we can start getting visible spectra of even objects fainter than 2022 WJ1 if we know to sort of be prepared. This is going to take some sort of teamwork in terms of how exactly we prepare as fast as possible. But for instance, at our big telescope, if you want to get the spectrograph set up, it probably takes about 15 minutes. That probably means that the second we hear about this, we have to call the observatory and tell them to get started on it as we're then preparing the observing plan. When we were observing 2022 WJ1, the telescope operator, the backup telescope operator, myself, and Nick Moskowitz, another co-author in the study, we were all working simultaneously to make sure we were pointing the telescope correctly. This was a situation where this object had a defined orbit, and it still took 4 of us to kind of get everything pointed correctly. I think building more automated systems, and I think getting the telescope operators trained to sort of be wary of these sort of strange circumstances, I think we're going to be able to do better and get more out of the fleeting time we have.
Thanks. They're pretty exciting. I'm looking forward to newer, more exciting results. Yeah,
I'm looking forward to being outdone.
Awesome. Well, thank you guys. If anyone else has more questions for Teddy, feel free to put them down in the chat and he's going to answer them. And I wanted to comment that, I remember when I talked to Nick about this, is that there are so many observations with a clear filter of the asteroid, but there's just nothing in any of the other filters. And the same is true for other observations. So the instructions probably for the amateurs would be, if you're observing this, try to snap at least a few pictures with different filters. That would be extremely helpful. Okay, good. Next up, we have Mark McIntyre. He's going to tell us about his effort to speed up the GMN orbit data pipeline. So, Mark, go ahead.
Okay, hopefully you can see my slides already.
No.
Oh, right. Okay, Zoom not shared them. Hang on a second.
Yes.
Let me see if I can get it to actually share them. I need to click the button down there. There we go.
Okay. Yeah, we can see the slides. Go ahead.
Okay, so as I mentioned in the introduction, I'm Mark McIntyre. I'm an astronomer and astrophotographer based in Oxfordshire in the UK. I'm media section director for the Society of Popular Astronomy and member of the UK Meteor Network and Global Meteor Network, and also a member of the UK Fireball Alliance. I am going to talk to you today about the problem that we've had with the performance of the GMN data pipeline and the work that we've done to speed that up. So, I mean, essentially the problem is pretty simple. As data volumes have grown, the pipeline has taken longer to process the data. During the PERSID last year, there were about 180,000 detections per night being made. And this meant that the solver was running sometimes weeks behind time. And it's very difficult for it to catch up because obviously it's got a huge backlog of data that it's trying to process and just can't get there. So at the end of last year, we started to look at this to have a think about what we could do to improve it. And what we've done is we have split the pipeline up using a kind of parallel and distributed processing approach. Now, this allows us to do the initial calculations much more quickly, often within a few hours of the data being uploaded, and then to refine the results later. The model that we've put together also supports distributed processing. And as Dennis mentioned earlier on in this evening's talks, part of what we're trying to do there is to reduce the dependency on a single server that we've got at the moment, and to distribute the load, more globally, in keeping with the kind of ethos of what we're going to do. So I'm going to talk through a little bit more about how we did what we've done so far and tell you a bit more about where we're hoping to go in the future as well. So this is a very, very simple diagram of the original solver. So the starting point for the solver is basically it goes and looks at all the data that's been uploaded for a particular 24-hour period, and the solver looks back over the last 6 days to make sure it doesn't miss anything. So it takes a 24-hour period and it analyzes all of the observations that have been made to find candidates. And a candidate is basically a group of 2 or more observations where the fields of view overlap, the times of the events are pretty much the same, and a few other simple checks are done to make sure that they're not, chance observations or aircraft or whatever. And so it goes through all of that data looking for these candidates. And then once it's got all the candidates, it then starts to process the candidates. And the processing itself has got a couple of stages, which I'll talk a bit more about in a moment. But essentially, it's doing an intersecting planes model, and then it's doing some more refined analysis to improve on the data to get a more sophisticated result. And at the end of all that process, it can then run the reports and it can update the website and all that kind of good stuff. The problem we really have is that first stage, that finding the candidates, can take anything between 30 minutes and 3 hours, depending on how much data there is. But the second stage, this can take between 30 minutes and 8 days, again, depending on data. So as I mentioned before, data volumes during the Perseids last year, nearly 200,000 observations on one particular night that I looked at, typically minimum of 10,000 observations on a really quiet night. And bear in mind that obviously the system is global, so we're getting data of 24 hours a day coming in. So you can see how this could take a very long time to process. But let's have a look at that in a bit more detail. Looking at that process data step in particular. Now, I drew it as a big single block before, but like I mentioned, what we've done first is we found a lot of candidate groups. And so really this process data step is a whole bunch of steps where we're looking at the first candidate group and we're solving that one. Then we're looking at the second candidate group and we're solving that one. And we're looking at the third candidate group and so on. In time order, we go through it in time order. And we do what we call a simple solution. And then we refine that solution by doing the Monte Carlo stage of the modeling. I'm not going to go into how the model works. You can read that in the papers that have been published if you haven't already. But we do that for every single candidate in turn. And so we're processing the data in time order. And you can see how if you've got like 10,000 or 20,000 or 30,000 of these candidates to work your way through, this could take a long time. Each of these stages individually doesn't take long. It takes 2 or 3 seconds to do this, the simple solution. And then it takes between 10 and 15 seconds to do the Monte Carlo stage. The time it takes to do each of these stages depends on how many stations are involved, what the sort of angles that the stations have are like, how complex the data is, the quality of the data. So it does vary quite a bit depending upon the data that's going into it. So we're doing this sequentially. We're trundling our way through all of these observations pretty much in time order, like this diagram here shows. And so, for example, it might take an average of 120 seconds for 5 candidate groups. The second block, the second Monte Carlo block here is slightly larger to indicate that it's a more complex solution. That's the only significance it has to the size of these. So what we did was we thought, okay, that's not going to work. It's taking too long. Let's take out all the Monte Carlo stages first. Let's just run all of the simple solutions one after the other as quickly as we can. And that immediately allows us to get those simple solutions 10 times faster than we were doing before. And that turns out to be okay, because a lot of the people that are consuming the GMN data just want to get solutions. They just want to know how many meteors we detected, what meteor showers they were in, a good approximation to their trajectories and their orbits, that kind of thing. So we do that, and then that lets us generate the reports and update the website much more quickly. In parallel, we run the Monte Carlo simulations. And again, because we're not waiting for those simple solutions to be run each time, the Monte Carlos can run faster. So even they can still run 30 to 40% faster, running in parallel. So we've achieved two things here. We've got much faster initial solutions, and that brings the timescales down from days to hours, which is exactly what we want to do. And the second thing we've achieved is that we've got the Monte Carlo stage, the additional precision and the uncertainties and all the more detailed modeling being done quicker too. And so all the data is still there, and we can get that initial set much more quickly. There's also some other advantages to what we're doing here. So the way that the first stage is working, this simple solution stage, is it's actually saving those solved results back onto the disk straight away. And so, as well as running the Monte Carlos on them on the same server, we can actually distribute that amongst different servers. Now, we're still working on this stage. There's still some work to be done here, particularly around the security model that we're going to put in place. But you could imagine that we've got multiple computers, multiple servers, not necessarily just within the university, but distributed globally, which can connect up, download some of those simple solutions, do the hard maths, the Monte Carlo simulations, and upload those fully solved trajectories. So we could perhaps, with 2 nodes, we could double the speed that we're doing the Monte Carlos at. And we could obviously, more nodes, we could do more. And this also lets us, spread the load, not just spread the load, but also reduce some of the dependence we've got on that single server that we've got at the moment. So going back again, here's our original solver that we started off with. 30 minutes to 3 hours for the first stage, 30 minutes to 8 days for the second stage, and then we can do the reports. Now we've got something more like this, where we're still taking 30 minutes to 3 hours to do that first stage. And I'm going to talk about that again in a minute. But now the second stage, we can do the simple solutions and have everything on the website within a few hours of the data being uploaded. And that's obviously a significant improvement. And we do now have this ability to spread the load of the Monte Carlo stage in particular, which is the time-consuming part of the data processing. Now, I've talked a lot about the processing part, but what about the find candidate stage? That's still taking hours to run. Well, there's some more work that we can do there, because again, what we're doing there is we're going through all of the observations in time order, and we're finding groups that could potentially be the same meteor. And so it's really also a set of individual steps, and each step, again, is finding a candidate, and then we're going off and doing the simple solution. Well, if we were to save those candidate groups straight away, rather than waiting until we found them all and then processing them, we could start the simple stage much sooner. For example, the first candidate, we could start the simple stage straight away after 3 or 4 seconds of upload. So we could bring the times down here significantly as well. And there's work that we're looking at the moment to see if we can work out the best way to do this. So we could basically save the candidates as soon as we found them, immediately start the simple process, and then in a third parallel thread, we could start doing the Monte Carlo. The other advantage here again is that we could then spread the simple solutions, could be distributed amongst other servers and other computing nodes. And we could again spread the load more globally rather than just relying on the one server in the university to do this. So that's it in summary. The initial solutions are, we've got this new version of the solver running. The initial solutions are now typically available within a few hours rather than several days of being uploaded. The compute stage can now be distributed, and we're working on the best way to do that. We're going to look at further improving the performance and in further distributing the processing. And really the end goal, as we said at the start of this, is the end goal is to reduce the dependence on a single server, on any single server, to spread the load more widely, to be able to run all of this processing in parallel so that everything can be not just done faster, but also distributed so that if there's a server outage or a failure or something, we're less dependent on one node to provide us all with all this data. So this work is ongoing. Whilst I've been on this conference this evening, I've been typing away in the background, doing some data and some coding, and I shall be carrying on doing that. So that's it. If you've got any questions, pop them in the chat or ask now, and I'll be happy to answer them.
Amazing talk, Mark. Any questions? We have about 1 minute. Okay, well, if not, then we will transition to our next talk. Thank you so much, Mark. Amazing work. And Dino, are you ready to present?
Yes, I'll share the screen now. I hope you see it now.
You're good to go.
All right, I'll start. So first, hello everyone. I'll be presenting to you 3 projects that I've been working on in the past year in the Global Meteor Network, with the accent on using the convolutional neural networks. Let's start first with the GMN MeteorNet project, which is about improving the meteor candidate filtering that RMS uses. So RMS uses a neural network as an additional check in case a meteor detector detects some false positives. The problem is that even then, it can still mark various artifacts on images as meteors. And what can happen is you see this line, which might look at first like a meteor, but when we zoom it out a bit, we can see that it is probably some buck trail that it detected as a straight line. So the goals of this project are to increase filters' capability to correctly discern real meteors from artifacts by training it on a newer dataset of images, and also to explore various model architectures and compare their performances to the currently used model. So here is a dataset that was used. For the start, I used 10,000 images of a much larger dataset from the GMN server. Detections were padded with 20, 50, and 100 pixels, and then results were compared. Convolutional neural networks can only work with a fixed image dimensions, so all images had to be resized to the same dimensions. And 3 of the dimensions were chosen and also later compared to see which one yields better results. And all pixel values on images were scaled to 0 to 1 ranges, as they usually work better with the AI models. For the metrics, F-beta score was primarily used since we can add an accent more on false negatives so that we reduce the possibility of losing some meteors, since that matters more to us. Accuracy was avoided since it isn't a good indicator of the model's performance when dataset isn't balanced, and we can't prioritize false positives or false negatives from one another. That metric looks the same at both of these. I also use for the models hyperparameter tuning, which means the algorithm chooses the optimized values of various parameters like image sizes, normalization layers, and presence of some layers. And for the training, for all of the models, 20 training epochs was more than enough. And for the training, 80% of the dataset was used, and the rest of the 20% was used for validation. Here are the results in 2 tables. In the first table on the left, you can see all the architectures and their performances in 3 columns for each image dimensions that were used. And on the right is the number parameter of each of the architectures used. More number of parameters means greater computation times for the pies. Here are some examples of mislabeled images. On the left, false negatives, which are meteors that the models usually may have mistaken for some artifacts, and on the right, false positives, which are mostly buck trails, airplanes, or various other artifacts, and there was usually more of them than false negatives. This is the model that currently works the best. When compared to the original model, it has a dropout layer with additional convolutional and max pooling layers with only one dense layer. This is its F-beta score, and its number of parameters is a bit higher than the current model. And this is the current model. With the currently used weights, it achieves a bit lower performance than the model that I have used. And when it is retrained on new data and new weights are acquired, then its performance is similar to the model I currently have. So in conclusion, models achieved best performances when median image dimensions were used. F-score is a preferred metric for unbalanced datasets. Padding of 20 pixels proved to be the best. Model that we currently use in the RMS has inferior performance with its older weights when compared to some newer models. And since models have to be deployed on Raspberry Pis, we need to carefully pick the balance between performance and parameter number. So in the future, I plan to add more sorts of images that were wrongly classified, increase dataset size if it proves needed, and improve performance scores in general. For the tools, I use Python programming language, TensorFlow framework, and Keras Tuner. And if you are further interested in the code beneath, you can check out my GitHub repository. Now for the SpriteNet project, sprites are atmospheric phenomena that have not yet been thoroughly researched, and in researching them, data from GMN cameras can prove very insightful, and it can show us how and when do these structures form. But to fully utilize this data, it is not enough to just detect if an image contains a meteor or not, but it would also be the best if we could detect where on images these sprites appear, and machine learning models happen to be the great for this task. I manually labeled over 2,000 images of sprites and have split them into two datasets, one which contains max pixel frames and the others contain detection only. And both of them had rescaled images to 320 pixels. For the model architecture, I decided to use the yellow architecture, which is popular in these problems. I choose a smaller model because we need to take into consideration that this would be deployed on Pis and they would do the computations. You can see below image how a training command looks like, in which we specify the number of parameters like epochs, image sizes, and batch number. For the training results, when both datasets achieved similar performances, and 250 epochs was enough for most models to achieve their peak performances. For the model implementation, since RMS also uses TensorFlow Lite module for meteor filtering, it can also be used for these sprites. Output of the models is processed in order to get the bounding boxes that we desire, which surround the sprites on each images. And also you can see here the SpriteNet repository if you're interested. For future plans, I plan to expand the dataset and the number of images with no sprites, since that way we reduce the number of false positives. And I plan to furtherly experiment with the model parameters. Now for the third project, this is a project that I did for a college, and it is a UI and UX design of a hypothetical mobile application called the GMN Station Monitor. The idea is that it offers a personalized monitoring of camera stations for the users and would notify them via push notifications if something goes wrong, camera doesn't upload or calibration has some issues. And this way we can have much less downtime. And this is the link to the project file and the QR code which you can scan to test the prototype. And just to clarify, there is no backend or front-end code. This is just simple design, and you can navigate between the screens to check out how the app would actually look like. And this is the showcase of some of the screens that I've designed. So the first one would contain all the cameras that you're interested in. You can also add them more if you want. On the second, we can see the detailed information about each camera's latest session. And we can also get the link to the currently Global Meteor Network's weblog for that night. And you can adjust your alerts that you want to receive. Do you want for regular upload or only when upload fails, or for all station statuses? And also optionally, option to have a profile and to back up your data when you transfer to a new phone. So I have to have also special thanks to Paul Rogermans for labeling Meteor dataset, Denis Vida for providing the dataset access, David Rollinson for Meteor model feedback, Sandy Barisic-Gota and Armir for providing sprite images, and also to my college professors Sanja Chanderlic and Ivona Frankovic Lucic for mentoring the GMN Station Monitor project. That will be all from me. Here is also my email if you later happen to have some questions or feedback about any of these projects. And thank you for your attention.
Amazing, amazing work, Dino. So I think I'm going to ask a question that's probably on everyone's mind, and that is, when are we going to see these features in RMS?
For the Meteor app, I would like to again improve some metrics, but yeah, I don't know when I would add them. I would want to maximize the performance as much as I can before actually implementing it, as it will be deployed globally. So I have to make sure that it will work in all scenarios as we expected, and that it would yield better performance than the current model. And the Spice project is still in development. I want to expand the dataset further to increase those metrics as well. And for the application, it is however the community seems fit. Do they need it? This is just a fun project that I did for the college, but if it actually proves useful to many of the Global Meteor Network station owners, I think it can also be realized. Since for the backend, this is mostly a web scraper, and the frontend is for the design part, it is already done.
That's amazing. So Luke has a question. Luke, go ahead.
Hey, amazing job, Dino. Are the weights combined in one? Is it one pass detecting the meteors and the sprite, or are they completely different projects? And would it be possible to combine the detection in one pass to get meteor and sprite detection?
I've also tried to use the YOLO network for meteor detections, but it has much more parameters than the currently used models, so I'm afraid that it would add too much load, since meteor filtering is, I think, done during the night, and it needs to be fast. And I think that if we can choose some lower models with lower number of parameters for the YOLO network, but I think they're still too high if we want to balance out performance and usability with the accuracy of the model. So for now, I have these two models. One is the YOLO network, and the other one for the meteors is much more simpler. But it also achieves a great metrics, 0.97. It is for now really good. So I think
it's amazing
that transitioning to YOLO network would yield more of the stress for the pies than the actual gain of accuracy.
Makes sense. Thank you.
Amazing. Thank you. If anyone has any other questions for Dino, feel free to write them in the chat or ask them during the next break. But now let's transition to Logan. So Logan, feel free to present.
Alrighty. Let me share my screen.
We can see the screen and you're good to go.
Excellent. Okay. So last year I gave a presentation about long-lasting optical meteor trails. This year will be similar, except now I'm going to compare them to long-lasting radio trails. So just for a brief overview of the optical persistent trains, these are going to be long-lasting, essentially clouds of glowing gas that are seen after some meteors, as you can kind of see in this little video snippet here, this 30-minute time lapse. Like the name suggests, these last anywhere from minutes up to an hour or so. And while we have a pretty good understanding of the emission mechanism, it's not entirely understood. However, the commonly accepted reaction is that metals from the meteor react with ozone in the atmosphere exothermically, and in the process produce light. The little image down here in the mini fridge is the camera we use to obtain the persistent train data that we then reference with the global meteor network. Okay, so meteor radio afterglows are very similar in that it's a long-lasting emission from meteors, except now in radio frequencies. So these were discovered about 10 years ago by my advisor, Ken Obenberger. While long-lasting, they don't last quite as long as the optical persistent trains, only lasting tens of seconds up to a few minutes. The image to the right here shows a video of a background subtracted MRA. The emission is broadband, unpolarized, and isotropic, which is consistent with it being self-emitted from the meteor trail, as opposed to being specular reflection from some sort of terrestrial transmitters. So far, we've observed them in high frequency and very high frequency, so about 20 to 60 megahertz. The emission mechanism for these is even less well known than the optical trains. However, two main theories exist, which involve plasma physics, Langmuir waves, and resonant transition radiation. I won't go into explaining those, but both of them require some source of superthermal electrons, which as of yet have not been identified. A theory exists that it could potentially be due to chemistry. So essentially, you have a negatively charged particle which reacts with oxygen in some capacity. These react, and an electron is ejected during the reaction, which would have sufficient energy to drive the radio emission. So we obtained our radio data from the long wavelength array in Savieta, which is in New Mexico. The bottom image shows the full array, all 256 dipole elements arranged in about a 100-meter ellipse. The top image shows it in a bit more human scale, these kind of bow tie shaped antennas. They're capable of observing between 10 and 88 megahertz, and of interest to me is the all-sky imager mode known as Orville. This has about 20 megahertz of bandwidth, 198 channels, each 100 kilohertz wide, creating an image every 5 seconds. The data I used came from a couple years ago, so we no longer have the full 198 channels. We were using archival data, so these have been averaged down to 6 channels, each of 3.3 megahertz. So you might ask, why would we expect these two phenomena to be related? They have vastly different emission mechanisms and occur at very widely separated wavelengths. So in 2020, Ken found 4 instances where persistent trains and MRAs were produced by the same meteor. And furthermore, the emission of each of these phenomena was co-located with one another as opposed to features in the parent meteor like bright flares. So this kind of gives a strong indication that there might be some connection between MRAs and PTs. So one proposed theory is that maybe the chemical reactions that drive the persistent trains could be responsible for producing those electrons that then go on to form MRAs. And that's sort of where my research comes in, where I created a catalog of persistent trains and MRAs in an attempt to statistically determine whether these two phenomena are related. So last year I presented on my catalog of persistent trains. It's been published since then, and it heavily used global meteor network data in the catalog. So in there we had about 4,700 meteors with 578 leaving trails that lasted longer than 1 minute, which is the rough guideline we use to classify it as a persistent train. So using this catalog, I then went and looked through the radio data in a directed search. So essentially saying, we know a meteor occurred at this time and place. Let's look in the radio data at the same time and place and see if we see any emission, which is vastly easier than doing a blind search. So the bottom image here is a snapshot from the GUI I created to help me look through these. In the teal panel, you can see radio images. The little black points there correspond to the start and stop of the meteor in the optical positioning from the GNM. And then you can also, GMN, yeah. You can also see the radio emission contoured as well. So this one has an MRA. In the yellow panel, you can see light curves in each of the 6 frequency channels. Frequency channel 3, the red line is the polarized emission. This was probably due to a reflection from some terrestrial transmitter. So not self-emission in that channel, but the other 5 look fine. So we had 2,900 total meteors located in this Orville data set as well. 675 had MRAs, 372 had persistent trains. So how did they stack up? Based on the Venn diagram, not all that great. Only a relatively small number of these had both MRAs and persistent trains, which kind of indicates they have no problem forming independently. You don't need to have an MRA to have a persistent train, and vice versa. So now the question really becomes, are these actually related at all? Or is it more like you're drawing to see whether it has an MRA, drawing to see whether it has a PT, and there's some probability you'll get a meteor that has both? So to do this, we just did a naive kind of chi-square test, created a contingency table here, found a very low p-value, which indicates that these are probably dependent processes. So one depends on the other, not super strongly, but there is a dependence. They aren't completely independent. So I say naive here because both of these phenomena are strongly affected by altitude. So the MRAs have no problem forming above 90 kilometers, but below 90 kilometers, they're strongly quenched, as you can see in the top diagram, where the orange bars show the peak height of the MRAs compared to the blue bars, the peak height of meteors in general. So there's a very sharp cutoff right around 90 kilometers. Persistent trains, on the other hand, exist in a very narrow altitude range, primarily governed by ozone. So you can see that in this bottom figure, where the blue curve is very narrow and shows the altitude ranges which persistent trains exist in, compared to the green plot in the background showing the general altitude range spanned by meteors in general. So even if we take these altitudinal considerations into account, there's still a dependence between the two groups. So this kind of leads us to want to play around in the parameter space and see what sort of parameters affect whether or not each phenomena occurs. So we can start this analysis by doing a principal component analysis shown here, which essentially is a way to reduce the dimensions of your data set from the 25 or so relevant parameters from the global meteor network down to the two shown in these axes. Even though it doesn't explain a large amount of the variance, it still is good at indicating that it looks like those that have MRAs and those that have PTs are decently separated, which leads us to consider using machine learning. So we use the gradient boosting classifier in order to try to distinguish between classes, and with that have about a 93% accuracy in distinguishing between each of the four different classes. It also tells us what features are important for doing this classification, including entry angle, which likely just encodes information about the beginning and ending height of the meteor, along with the ending height, the mass, the duration, and the average speed. So this is potentially very exciting because it indicates we can use data from the global meteor network, feed it through this machine learning algorithm, which will spit out whether there's likely to be a persistent train or not, or MRA. And then we can point the whole suite of instruments that we have ready to deploy at the Air Force Research Lab, including an astrograph, spectrometers, hyperspectral imager, all those with very narrow field of views but high spatial and temporal resolution. We can point those to the location of the meteor and start recording. However, the problem with this is that we would need to be having this global meteor network data in near real time, which currently could be a problem, but maybe would be able to be sped up by the improvements we heard about earlier, which would be really great for serving as a way to trigger on these events. So just the main takeaways here is that while persistent trains and MRAs are statistically significantly related, it's not as close as maybe was previously suggested in the literature. And then we can also potentially use data from the global meteor network to serve as a trigger for steering high sensitivity instruments in order to further study this phenomenon. That's all I have. Thank you.
Amazing work, Logan, as always. Are there any questions for Logan? We have some time because our break is going to begin soon. Okay, well, if there are no questions, I mean, I can definitely comment on whether it can be done in near real time. Oh, okay, Luke has a question. Okay, Luke, go ahead.
It was just about the real-time requirement. I was curious if it was you would require that by your sensor only, not the whole network. Is that right?
Right. So we'd probably just need the few cameras in central New Mexico that could reasonably see the meteor to be at least providing a basic trajectory with entry angle, mass, that sort of stuff. It doesn't need to be super sophisticated. We aren't trying to catch necessarily every persistent train or MRA. We just like to catch at least some of them, essentially.
And we talk about how quickly, like within a fraction of a second, or?
So the trains themselves last minutes to hours. Ideally, within a minute or so would be ideal. Sooner than that would be great, but at least sub-minute time scales would be really helpful. Yeah.
Thank
It
you.
can definitely be done. Yeah. So the detector pretty much runs in real time. So the FF is collected and saved every 10 seconds, and then the detector does the detection. So within, let's say, less than 20 seconds, maybe even faster, I think it would be definitely possible. Then it just needs to be reported to the disk, and that's when you have the direction locally. So you can at least, I don't know, like pre-queue the system if you have a camera on site. And then in terms of getting the full trajectory parameters, if you need something rough that doesn't have uncertainties and doesn't really run the full model, you can run something only using, let's say, like intersecting planes, which is going to be good enough. It's going to give you good enough results, and that can be also computed in a few seconds. The pipeline for that would need to be set up, and some things would need to be modified. But I mean, I'm gonna put it, the Lego pieces are there. It just all needs to be connected together in a meaningful way. So I think it's definitely possible.
Awesome. Thanks.
Awesome. Good. Well, we have about a 5-minute break when Oriana Gall is going to tell us something about the Draconian meteor shower. Until then, feel free to walk away, do whatever, or talk to people you want. I am going to open breakout rooms for the next few minutes. So if you want, just kind of pull your speaker that you want to talk to by the hand, and just take them to the breakout room, talk to them, and then come back in 5 minutes. Okay, okay. Here we are again. Jamie, I think we were in the middle of a discussion about the implementing these things into WMPL, and you say you already have a modified version. Yeah, I mean, I'd be happy to implement things. So one thing that I'm wondering is the wind correction. Are you taking the atmospheric mass density into account? And by that, I mean, sorry, I don't want to interrupt your meal. Um, uh, definitely like up high at, 100 kilometers, there's not much of atmosphere to speak of, and there's more deeper down. And that has an influence, and it's interfacing with the fireball in one way or the other. Are you taking that into account, or is just the correction applied across the scale?
We're not using any kind of wind model at all.
Okay.
It's purely based on the lag curve. We're
Okay.
using the lag curve. It's just about frames of reference. It's about you're decelerating in a frame of reference that is moving with respect to where you're doing the calculations. So it's Earth rotation velocity, and there's only a couple of seconds where it's traveling between 50 k's height, where the air is very thin, and 30 down to 20 k's height, where it's getting thick enough to make a difference.
Mm-hmm.
It's where you start to see the lag really piling up.
Mm-hmm.
And it would seem that the velocity of the winds up there in terms of meteorological winds is pretty consistent. You don't get rapid reversals of wind direction between those height ranges. And also we're fitting to actual measured data.
Mm-hmm.
So I'm looking just to see if it improves the fit at the end of the trajectory. If that's achieved, if say you manage to bunch all the data points of all the different camera measurements into one 100-meter tunnel, then the job's done. Is to get rid of all these wild swings and swerves that can run to several hundred meters of residual. That's what I'm aiming to eliminate. And there could be some variation. Obviously, the wind might, I'm using 30 k's height, the 10 hectopascal level. But there might well be models out there that can give you a mean of wind speeds, say in the range 30 to 50 k's height. But from what I can tell, it
Sorry, I have
goes
to run
in the
back
same direction.
because our speaker is going to start in very soon. But let's continue this discussion after the next session. Sorry about that.
I know. Cheers, Dennis. I've got a cat too.
Yeah. Let's see. Ariane, I think you're good to go.
Okay. Can you see my slides?
You're all good.
Okay, great. So, hi, I'm here to talk about forecasting the draconic meteor shower. You probably all know this shower, but I'm just gonna recall a few things about it. The draconids occur early October. It peaks around 8 to 9. It has actually a very short peak, lasting for about 3 to 4 hours, with 75% of the activity happening within an hour. Draconic is very irregular. Most of the years, you won't have a lot of meteor activity. We're talking ZHRs below 1, but occasionally it displays strong outbursts and even storms. The parent body of the draconic meteor shower is comet 21P Giacobini-Zinner. The comet was first discovered in 1900 and then rediscovered by accident in 1913. And it's a Jupiter family comet. And actually, its orbit is very, very perturbed by the giant planet. And so its evolution is called erratic. Shortly after the comet discovery, Davidson suggested we can expect some meteor activity from 21P. And indeed, in a week, draconic activity was observed in 1926, confirming the association between the shower and the comet. Then we had no draconic observation until the two huge storms of 1933 and 46, when rates of 5 to 10,000 meters per hour were reported all across Europe. In the following decades, as I mentioned, sometimes we had no draconic activity at all. Sometimes we have strong outbursts like in 88, 2011, 2018, or even storms like in 1999 or 2012. So you see that the shower is very irregular. And what's interesting is that for some apparitions, we only have observations made with radio instruments, while other apparitions have are more significant in the optical range. So we have obvious signs of mass segregation within the stream. So the Draconid is a good example of meteor showers that space agencies don't like. Most of the meteorite threat to spacecraft safety comes from the sporadic background, but showers that are able to produce thousands of meters per hour can significantly exceed the sporadic flux for short periods of time. And for example, for the Draconids in 2012, we had more than 3,000 meters per hour that were reported. So this shower poses a risk for space missions, not only at Earth, but also in its surroundings, like at the Lagrange positions where we have some spacecraft that are stationed. So in the past, this stream encouraged spacecraft operators to implement mitigation strategies. For example, in 2018, the European Space Agency decided to change the orientation of the Gaia satellite for a few hours to reduce the potential damage of an impact with a Draconid. But as you know, these mitigation strategies, they're costly and they also incur risk for the space mission. So that's why the space agencies need to have accurate forecasts of the shower's timing and intensity. The problem with the Draconids is that it's really hard to forecast. In the table on the left, I'm just going to summarize a bit how the quality of the predictions that were made over time. So we're going to have the apparition year, the intensity of the shower, whether we expected it or not, and the quality of the timing and the intensity prediction. So initially, all the forecasts we had were based on the motion of the parent body. The idea is just to say we expect the draconid to appear when comet 21P crosses the ecliptic plane near the Earth. The problem is that with this method, you don't have any intensity estimate for the shower. And as we can see, it also had a mixed success in predicting the time of the shower. Actually, except for the very young outburst and storm, this method is unable to predict the time of the draconid apparitions. And that's because the meteorite streams released by comet 21P do not evolve like the parent comet. At the beginning, the meteorites are ejected from the comet surface with a non-zero ejection velocity, so that will induce a change in their orbital period, and as a consequence, the meteorite stream will stretch along the parent comet orbit. But the combined influence of radiation forces, planetary perturbations can really alter the structure of your stream, and that's what's happening with the draconids. What we see here is just a simulation of how a trail ejected from the comet in 1900 evolved with time. And so we see that at the beginning, the trail starts stretching along the comet orbit, but in only a few decades, because of planetary perturbations, we start having gaps and very complex structures in the stream. So we can forecast the draconid just based on the motion of comet 21P. That's why we love numerical simulations, because full dynamical simulations of meteorite streams enable to account for all these tricky orbital effects fairly easily. All the stream models are based on the same steps. The first one is just to identify your parent body, integrate its motion back in the past, then you generate your meteorite stream. So you eject the particles that you integrate up to the present. You select those particles that will produce a meteor. And so by analyzing these particles, you're going to create your simulated meteor shower that you can compare with meteor observations. The first trail simulations that were done for the draconids was for the 98 apparition, when Reznikov and Kresak were able to accurately predict the return and the time of the 98 draconid outbursts, but the intensity estimate was off by a factor of 10. And after that, unfortunately, the modelers missed the apparition of the 99 radio storm and the 2005 radio outburst that was observed by the Canadian meteorite orbit radar Seymour. And we had to wait until 2011 to have our first complete success in draconid forecasting, when Watanabe, Sato, Bobayon, and other modelers accurately predicted the timing, the duration, and the intensity of the shower. So that could have kind of definitely settled the case for a shower. But as you know, in 2011, we had this huge radio storm observed by Seymour that was completely unexpected. So that's why we started working again on a new model of the draconid. This is a work that's been done in collaboration between the Western Meteor Physics Group and the Meteorites and Environment Office. And I'm going to show some results from my simulations and the simulations from Paul Wiegert and Daniel Moser. So we developed a new model in 2018 that we refined last year, and we're currently working on it. The idea of our simulation is really to model more realistically the past of comet 21P. So it's ephemeris, but also it's dust projection. And we're trying to focus not only on the timing and the radiant of the shower, but we're trying to reproduce the activity profile of all the past draconid apparitions. And to do that, we have to calibrate our simulations on all the meteor observations we have in optical and radio range. And for this model, we are actually trying to reproduce the characteristics of 10 past draconid outbursts. I'm not going to go through the details of the model, but I can maybe just talk a little about its current performances. So for these 10 apparitions, we're able to reproduce the correct time of 9 of them with an accuracy of half an hour. And we're also able to reproduce the intensity and the activity profile of 6 apparitions. This model had some interesting successes in the past. So all the simulations are the boxes in the following plots, and the rest are observations. For example, from our 2018 simulations, we're able to kind of predict plus dict the Draconid storm of 99, because we had this strong signal in the simulation for 99, but no observation of the shower. And despite all my efforts, I wasn't able to remove the strong activity we had in our simulations. And when we looked into the data a posteriori, we found the Draconid storm in radar data. So that was very exciting. Our model was also able to produce the best forecast of the 2018 apparition of the shower, and also predicted successfully the 2019 radio outburst. We also have some failures with our current simulations. The first one is that we're unable to explain the outburst that was observed by Seymour in 2005. And for two other apparitions, we're actually underestimating the shower's intensity by a factor of 4 to 6. So we haven't found yet this perfect solution explaining all the characteristics of all the past Draconid outbursts. We're still searching for that. The problem is that our search is hampered by two things. The first thing is that we have uncertain flux measurements for most of the Draconid apparitions. And the second one is that the shower has an extremely variable mass index, not only from apparition to apparition, but sometimes even during the course of the main peak. Luckily, a few months ago, we had a surprising development that may help us with this search, and that's the Draconids in 2024, because several instruments reported an enhanced Draconid activity on October 8 with optical rates of about 15 meters per hour, which is stronger than what we predicted. The shower was really well observed by GMN, and thanks to that, we have a complete flux profile for the shower. So thank you very much for that. The apparition of the Draconid was also detected by several radio instruments that suggest that the activity was probably higher in radio range and 45 minutes before the optical peak. So maybe the instrument detected a different population of meteorites than what GMN did. And what's interesting with the 2024 activity is its age, because previous simulations from Jérémy Vaubaillon indicate that maybe this activity was produced by a trail ejected from the comet in 1952 or 59. And in my model here on the left, so my model are the red boxes, we see that most of the activity comes from the 1900 trail. And actually, the predicted time with this model is very close to the one that has been reported by the radio instruments. So when we think about it, it's just the first time since 2011. For the first time, we have these high quality measurements of meteorites ejected by the comet around 1900 or prior to that. And this is a period for which we don't really know where the comet was. So we're really hopeful to be able to use these observations to constrain the path ephemeris of 21P and improve our forecast for the shower. So very quickly, I'm going to go with the conclusions. You understand that the Draconid meteor shower is a very complicated forecast. I think the table on the left speaks for itself. But we've developed a new numerical model of this stream that reproduces well most of the characteristics of the past Draconid outbursts, at least within the observational uncertainties. But we haven't found yet this perfect solution explaining all the characteristics of all the past Draconid outbursts, and including the radio outbursts that have been observed in 2005 and 2012. Hopefully, we hope, and I think we have good chances to be able to use the 2024 observations to help refining our simulation. And that's what's keeping us busy currently, because actually it's important, because we are predicting a very strong return of the shower in 2025 on October 8th. The predicted rates vary from a few tens to a few hundreds meteors per hour. So we're talking about an outburst here. Most of the activity is expected to occur in the radio range. We're talking about like some millimeter sized particles, but it's going to be very important to observe that shower and to confirm our predictions or help us refining our forecasts. So we really hope that the GMN community will remain mobilized to observe the meteor shower next October. Thank you.
Amazing talk, Oriane. Thank you so much. Are there any questions for Oriane? Okay. Okay, well, if there
Okay.
are, please put them in the chat. Thank you so much, Ariane, and we're looking forward to October.
Yeah,
Well,
fingers crossed.
absolutely. Well, we'll make sure that the cameras are running.
Thanks.
Thank you. And Luke, go ahead. We can see your presentation.
There we go. I'm coming online. Hello, everyone.
You're good to go.
Good to go. All right, this is a follow-up on the presentation I did last year. So last year I introduced this idea of a project to the community, and so this is an update of what's happened since then. So after the presentation I did on GMN, I did a presentation to the contrail researchers in London, and where I pitched the idea of using GMN cameras to do contrail observation for research. That was extremely well received. It really answered a need that the research community has. So they need a contrail data set to validate the model prediction, which they don't have. So being able to build such a model would be fantastic for them. So also we were able to raise some money out of this. So I think I can report that Google Research and Breakthrough Energy have been giving us generous grants for this research that the University of Western and Dunis are able to utilize, so that we can make this research sustainable. We are actively applying for additional grants. What we've been doing, or especially what Dunis has been doing with this money, is that we've been able to hire interns. So I don't have a picture of all our interns. I'm sorry for Jerome, Andrew, and Dan. So you may have heard Madiam's name floating around. He's been working on the code, on the RMS code, and that's a direct result of that influx of money from Google and Breakthrough Energy. So what are we talking about here? We're talking about contrail observation. So why do we want to do that? So for those who didn't hear my introduction last year, I'm going to do a quick recap. So aviation is responsible for about 3.5% of man-made global warming. 2% of that is, with high confidence, is coming from the CO2 emission. The rest, the consensus is about 1.5–2% is coming from a non-CO2 effect of aviation, and specifically coming from the warming impact of condensation trail behind aircrafts. So contrails is responsible for half of the aviation warming impact, about 1.5–3% of anthropogenic warming. Of those flights, only about 2–3% of flights are causing about 80% of the contrail energy forcing, which is, it creates a very low-hanging fruit for us to act on. So if we can act on 2–3% of flight to essentially cut 2% of global warming globally, I believe we have to do something about it. It's an opportunity, probably the best opportunity that we have to cut this amount of global warming. So we can cut it also rapidly. We don't need to change equipment. We don't need to modify airplanes. It's also fairly cost efficient, maybe one of the most cost efficient way to remove this amount of carbon dioxide equivalent out of the atmosphere. So we're talking about 1 gigaton of CO2 equivalent per year. Also, unlike cutting CO2, which we still need to do, cutting contrails emission or reducing contrail formation has an immediate effect on the global warming. So what are contrails? This is the definition, essentially. We're talking about ice clouds, man-made ice clouds. They're just made of water ice. So where's the water coming from? So the water in the contrail is mostly coming from the atmosphere. We form contrails in ice supersaturated region. So the water is already present in a supersaturated form in the air, and the extra water from the combustion of the carbohydrate plus the influx of salt and aerosols, which provide a condensation nucleus, causes the moisture in the air to condensate and form ice crystals. So per kilogram of fuel burn, we produce about a little over 3 kilograms of CO2 and a little over 1.2 kilogram of water. So it's the hydrogen in the carbohydrates immediately recombine with the oxygen to form water. So yeah, it's just a cloud. It's just a cloud made of water. So why is it a problem? So it turns out that aviation-induced cirrus clouds have a very strong warming effect. It's a greenhouse gas, essentially, a greenhouse effect. So they absorb long-wave radiation and they trap long-wave infrared radiation. So why cirrus cloud in particular are a problem? So here we have a temperature of the standard atmosphere. And aircrafts fly at about the 10-kilometer mark and above, and that's also where cirrus clouds form. So cirrus clouds are the coldest forms, the coldest clouds there is. And why is that a problem? So I'll talk about that a little bit later. So we have the cirrus clouds have a paradoxical effect. On the one hand, they reflect shortwave radiation back to space, which is cooling. But on the other hand, they trap long-wave radiation, which has a warming effect. The net impact is a strongly warming effect. So the Earth is in thermal balance. It receives about 1,361 watts per square meter of solar radiation over the disk that it presents to the sun, and radiates the energy back to space on the surface of the sphere at about 340 watts per square meter. The surface of the sphere is about four times the surface of the circle, the disk. So it balances out. What do contrail do? They increase the amount of high altitude cirrus clouds, which are very cold. And what we want is to have the Earth as bright as possible in the infrared spectrum. So a cloud that is very cold, as you can see these dark areas on these pictures. Those are cirrus clouds. So cirrus clouds are cold and very dark in infrared and block the outgoing long-wave radiation, which has a warming effect on Earth. So we want to reduce the amount of very cold high-altitude clouds. So here is infrared image of contrails. As you can see, they are darker because they're cold. And okay, there's a box right over some contrails here, but there are more contrails here on the left as well. You can see that they would have a warming effect on Earth. So we have several types of contrails. Short-lived contrails, which disappear very quickly, have basically no effect. Persistence, non-spreading contrail also have very little effect on the climate. Persistent spreading contrails, contrail outbreaks, and then we have contrail outbreaks that basically form serious clusters that are completely indistinguishable from natural forming contrail of natural cirruses. So what can we do about it? Well, we would like to change the flight path of about 2% of flights. So, and by that we mean simply changing altitude. We do that every day for turbulence. We typically descend 2,000 to 4,000 feet to avoid turbulence, and we can easily do the same to avoid contrails if we can predict where we're going to form a persistent spreading contrails. We can also act on the aerosols coming out of the engines to reduce the formation of contrails. So there's a lot of work in that area. If we do change path or altitude, we burn more fuel, so we would increase our CO2 emission. However, the warming effect on of these persistent spreading contrail is so much greater than the CO2 effect that it's well worth doing it, even if we get it wrong, maybe 9 out of 10 times. If you get it right 1 out of 10 times, it's still worth doing. As of January 1st, 2025, the EU is mandating that all operators monitor the contrail, the contrail effect on the flight. So what they have to do is airlines in Europe, as of January 1st, plug in all the flight data into a modeling software which predicts the amount of warming from the contrail, the non-CO2 effect. However, there's a huge challenge. The challenge is model validation. We don't have a good data set on which we can compare the prediction of the model to the data set. So we don't have a flight to contrail data set that's robust enough. And why is that? Why don't we have a good model, a good data set? Here's an example of model prediction versus so in white you have contrails predicted to have existed versus in red contrail actually observed. However, we don't know those red detected contrails. We don't know what flight have produced these contrails, so we can't build a data set out of these images. The issue is that contrails are not visible in satellite images until they are about 1 hour old. And by that time, it's very, very difficult to associate them with a flight. So for example, here's an attempt to associate observed contrail to known flights, and it's very, very difficult to do on satellite images. So the idea is to use ground-based cameras to observe contrail at the moment they are being formed and clearly associate them with flights. We could then pass that on to satellite imagery and monitor them for the lifetime of the contrail. It could be up to 14 hours. And then create a database on which contrail climate researchers can compare the model output to this database. So here's an example of what it would look like. So this is a GMN camera image with machine learning detection of contrails, which is then overlaid on a map. We have since the GMN cameras are already calibrated, it's fairly easy to know exactly the position of these machine detection of contrails. So what we've been doing the last few months with the Google and the Breakthrough Energy money, we've purchased some software, and with the help of the interns, we've been labeling a whole lot of images, and we started to train an algorithm to detect contrails. So this is an example of the hand labeling we're doing right now. And we are overlaying these machine detected contrails on a map along with the detected contrails from geostationary images and the field of view of our cameras. For example, here you can see the red detected contrails touching a field of view from one of our cameras, and then we can click on these detection and see what the camera sees. Hopefully, I think the plan is going to be to make this map available online so that the operators can see what the camera is being used for. So right now, RMS is collecting night time lapses for the purpose of contrail observation. The ask is that if your station has the capability to do so, to turn on the day and night observation. For that, you would have to go in the config file and turn on continuous capture to true and switch camera mode to true. There is a cost to you, the operator, and to the meteor observation too. First of all, the Raspberry Pi, if that's what you're running, needs at least 4 GB of RAM. It does consume disk space. It's currently a pain point. It consumes too much disk space, and we're working on reducing that impact. And it's only been tested on IMX 291. And it's still in development, so there's maybe risk of less stable environment. But we ask that if you are so inclined to consider turning continuous capture mode and switch camera mode to true in order to gather 24/7 data. So I'm sure most of you have seen this. This is the last NASA global temperature recording. So we are in a rapidly warming climate, and I think if there is anything we can do to mitigate this problem, anything in our hands, that we should consider doing it. The last 2 years have been especially worrisome. And I think my time is up. So I can stop here.
Thank you. Well, you actually have a few more minutes.
2 more minutes. Okay.
If you got stuff, just take.
No, that's okay. So the road ahead is we're going to develop the machine learning further and automate the contrail detection and do the flight matching. So hopefully by this time next year, we'll have actual data to share, data set to share. And a quick quiz if I have 1 more minute. I gave the answer already. This person here, 1919, was the first person to lay a contrail. It was a high altitude record. They were testing a new BMW engine. They went to 32,000 feet. He did a little turn, looked behind himself, behind the airplane, and noticed a white trail. And that's one of the first, if not the first, report of a contrail that we have. And with that, if you have any questions.
Amazing. Thank you. Are there any questions for Luke? So this has been a big effort. It's been occurring for a good part of the year. And yeah, Pete Eshman, go ahead.
Yeah, I'm wondering, could planes have a camera in the tail section that would detect their own contrail and possibly alert the pilot that they were producing a contrail? Is that feasible or not?
No, there isn't such a thing. And even if it did, it would only see the contrails on a very short distance. So it wouldn't really tell the pilot if it was a problematic contrail. It could be a very short-lived contrail. There are plans to install humidity sensors on board airplanes that could indicate, give us more information, and that's costly. There are also long-term plans. Well, I don't know if they're plans. There are consideration to launch a satellite constellation at the tune of several billion a year in terms of money to monitor contrail in real time. But nobody has signed off on the dotted line, and if at best it's decades away. So no, the one of the visual indication pilots have of a contrail is they can observe the shadow of their own contrail if the sun angle is just right. So from the cockpit, you can see your own contrail in your shadow, essentially. But that's about it.
Thank you.
Paul, go ahead.
Yes, Dennis, you forwarded a request for access to our camera data from, I think, a similar project from the European Coordination Center. Is this related, or is it completely different project?
Yeah, absolutely. So this is all related, and we are talking to pretty much almost everyone in the world who is doing this kind of research. So that includes people at Google, at Breakthrough Energy, and at Eurocontrol, Imperial College London, and a few other people. Everyone is extremely interested in our ground-based data because it is the only data set of this kind where we are happy to make it open, contribute to the community, and also we have really good calibrated imagery. So the whole point with the recent software changes is to just make sure that we have 24/7 observations. And of course, because this data is a bit different from meteor data, and because individual imagery is shared, we contact operators directly before any time lapses and imagery is shared. So yes, we're collaborating with quite literally almost everyone in the field. Okay, good. Well, thank you.
Thank you.
We're gonna have amazing talk, Luke, and we can discuss more about this topic during our Q&A and the unstructured workshop. But for our last talk of the first session, we have Pete Eshman. He's going to talk about changes to the brand new RMS images and the multicam setup on Linux and the Pi 5. So Pete, feel free to share your screen and go ahead.
Okay. I guess that's working.
Yep, we can see your screen. You're good to go.
Okay. Okay. Thank you. My name's Peter Eshman. I'm trying to get my screen to scroll here. I guess it's not doing it. Hang on a sec. That one. Okay. Luke Busquin provided.
Pete, sorry to stop you here. We seem to see half of your screen for some reason.
Okay. All right. Let me see if I can fix that. Is that better?
That is better. Yep.
Okay, great.
Okay, go ahead.
Luke Busquin provided observation summary totals from January 30th. 66.5% of our hardware is running single cameras. Combining Pi 5 with Linux, 28.8% of our cameras may be on multi-camera systems. I've combined Pi 4 and 400 for 655 cameras, which represent 86.4% of our single camera system. Perhaps 500 to 600 of these are running Buster, and they lack OS support. We have a few cameras on Bullseye, which has legacy status. That means they will lose OS support in 2 years or so, when Raspberry Pi releases the next OS version. 3.8% of our cameras are running on Pi 5 running Bookworm, which is the version recommended by Raspberry Pi for all hardware. This OS release pattern is held for years, so GMN contributors should upgrade to a newer release sooner rather than later. Fortunately, Raspberry Pi's new releases are compatible with earlier hardware. GMN's challenge is making RMS forwardly compatible while retaining support for older hardware. We should encourage people to upgrade to new versions to help them avoid problems and reduce support load on our GMN volunteers. We are working on a revised Bookworm image. It will include OS and RMS updates. It'll also include support for Pi 4 RTC modules and RustDesk for connections to remote stations. This new image will target RMS for both Pi 4 and Pi 5. Why upgrade? Old versions may have less support from Raspberry Pi and RMS. A shrinking RMS user base for your version means fewer people reporting problems and solutions. You may see inefficient data processing and more errors. Old versions don't support new features like GStreamer, machine learning, full camera configuration, and so on. Aging hardware may be an issue. If there's red in your FF interval plots and log entries show 1 second or higher frame age, your microSD might be worn out, or storage space might be too small for multiple capture directories. You can add a larger microSD or upgrade to a USB drive, which is also a great opportunity to upgrade your RMS version. Perhaps the Ethernet port, Wi-Fi, or USB ports are failing. If so, you can add USB hubs or USB to Ethernet and Wi-Fi adapters. Be careful because on some Pi hardware, the USB 3 interface can interfere with Wi-Fi or other functionalities. Perhaps your system may not have enough RAM to support new RMS features. For failed hardware and lack of RAM, the only recourse is to replace the hardware and update your version of RMS. For Pi 3, you could upgrade to a used Pi 4 or new Pi 5 or a recycled Linux PC. For Pi 4, you could upgrade the RMS version going from Buster to Bullseye or Bookworm, or upgrade your hardware. If you're upgrading hardware, consider whether you might want to move to multiple cameras on a single platform. For upgrades, the first step is to run scripts RMS backup from a terminal window. This creates a zip file in your home directory containing your most important files. Copy this file to a USB thumb drive for safekeeping. It's really good insurance to do this even if you don't have plans to upgrade. If you're thinking about hardware or RMS image upgrades, consider also if you want to run more than one camera at your location. Carefully research the cost of a refurbished PC before assuming that a Pi 5 is your best option. Pi 5 costs between $60 to $120, but after adding a case, cooling, power supply, and a micro SD card, an 8 gig Pi 5 is $130 total. Pi 5 allows to use NVMe storage, but that's an extra $65 for 512 gig. Adding NVMe now increases the 8 gig Pi 5 to $175. Refurbished Intel i5 PC costs about $150. But what about your old laptop or other system that could easily run RMS on Ubuntu? An Ubuntu PC is the best solution for lowest cost and greatest capability. They use more reliable storage media, avoiding the somewhat troublesome microSD of the Pi. Raspberry Pi probably chose microSD storage because it made the hardware cheaper, not because it was the best for long-term use. If you're moving to multiple cameras, you have two options. You can run 2 to 3 cameras on a Pi 5 or run 6 on an Ubuntu PC. I say 2 to 3 cameras on a Pi 5 because some people are running 3, but I've only been able to get 2 running using the GSD media backend. Both hardware options use scripts that help you add cameras. They use the same directory structures and provide the same utilities. Both provide desktop shortcuts for CMN bin viewer, along with show live stream and start capture for each camera. The install script for RMS on Ubuntu PC tries to match the look and feel of Pi RMS. Currently, we support Ubuntu 20.04 on PC. We recommend this Ubuntu release to avoid whaling graphics that interfere with remote connection software. 20.04 was released in 2020 with standard support ending April of this year, but free Ubuntu Pro support lasts until 2030, with legacy support ending in 2032. Ubuntu Pro support is free once you create a free Ubuntu account. Ubuntu 22.04 is newer, but it really only adds 2 years to these support end dates. The conflict between Wayland and remote control software will probably be resolved soon. RMS support for new versions will also improve. We may be able to do in-place upgrades to newer Ubuntu release versions later this year. In fact, some of our more experienced Linux users are already running RMS on newer versions of Ubuntu. Our challenge is to make RMS run on the new Python that is bundled with newer Ubuntu. You don't need much of a PC to run multiple cameras. During the 2022 GMNs, with average counts of 634 in the detected stats, I recorded second and third streams from 3 primary cameras for a total of 6 cameras on a low-end Celeron. At this time, the particular Celeron system cost $240, not including the 1 terabyte M2 drive. Now the price has dropped to $160. I used my 10-year-old i5 HP Elite desk as a benchmark, recording the primary streams on the same camera. In other words, I recorded 3 streams on 3 cameras for 9 cameras split between the 2 Ubuntu PCs. The Celeron recorded the same amount of data, but just took an extra 3.5 to 4.5 hours to finish processing the next morning. This live data test proves that a low-end 8 gig system is good enough to record 6 cameras under a very heavy media load. Another fairly active night averaged 132 per detected stat, and the 6 camera Celeron took a little over 2 hours longer to finish processing. On a normal night with fewer meteors, the 6 camera Celeron takes 1 to 2 more hours in the morning. This extra processing time over that of a 3-camera 10-year-old i5 has no impact on the quality or quantity of recorded media data. Here's a detailed information about my 2 systems. I won't go over all the boring details now. I'm including this slide for future reference in case anyone viewing the conference recording would like to pause to inspect all these details. Regarding MCAM and multicam in general, my experience is that it's much easier to manage multiple cameras on a single system than it is to manage a bunch of single camera systems. On the left is a single camera directory structure, and on the right is the multiple camera data structure. Once you move to multicam, a number of things come to mind. The old designation of station ID shifts to camera ID. with multiple cameras located on the station. We could move common config parameters such as lat long, elevation, and other static values to a single config file for station, and then use smaller config files for camera-specific settings. We might want to move our single camera Pi to the multicam structure, providing a smoother transition to multiple cameras later. Pi 5 are the best choice for those who are just starting out with GMN, and they support more than one camera. New GMN contributors could start out with a multicam data structure, and then moving to multiple cameras becomes a logical extension. I'm sure other changes will be needed as RMS continues to develop on new hardware and software. Thanks for your time, and I'm happy to try to hear any comments and answer any questions.
Thank you, Pete, for a wonderful talk. I think this is going to generate a lot of discussion. So let's maybe if someone has any questions for Pete, feel free to go ahead. And then after a few minutes, we're going to take a group photo. And after that, we're going to start our Q&A and unstructured workshop where you can ask whatever you want. I don't have anything prepared for the workshop. It's pretty much whatever people have on their minds, and we can discuss about any topic. Okay, any questions for Pete?
Hi, Pete. Good talk there, thank you. I just had one there in the chat about kind of an idiot's guide on how to configure a Pi 5 for two cameras. As I think you correctly alluded to there, it's the system. Oh, that's what technology has advanced. We're at the stage now where the hardware has overtaken the camera, and we can now configure more and more. And I agree completely. It does make sense to align it to be more plug and play friendly for more than one. Yeah.
Okay, thank you.
I suppose is there plans for a write-up maybe on how people who are not used to Pi software can actually plug in a second camera? Is that something that's easy to do now, or will it need a new update to the software for people to be able to do it?
Okay, for those that are running the bookworm image that's already been released, there is a script that's supplied automatically through RMS Update that people can run that will prompt them for another camera designation, at which point it will convert the system to the multicam structure and allow them to add additional cameras. They have to answer a series of prompts as they go through that. We are in the process of trying to provide a little bit better documentation for all of this. At which point there will be more in the wiki, the GMN wiki, to help people with the newer bookworm images and some of the things that have changed with that development. Obviously, that's really the road going forward. And the sooner even old single camera systems move in that direction, probably the better.
Yeah. Great, thank you.
Pete, any other questions for Pete?
Yeah, Pete, I have a question.
Yes.
About what is your experience with the updates from Ubuntu?
I'm sorry, I don't quite understand. My experience with Ubuntu updates?
Yeah, correct. So Ubuntu will also update, same as Raspberry does from Bullseye to Bookworm and so on. So you say you use Ubuntu 2004, but I think
yes,
there are different versions now, later versions of Ubuntu.
There are later versions, but they use Wayland graphics, which causes problems for remote control software. I know people are running RMS on Ubuntu 22.04, but they're having to do a few tricks to do that, and we haven't standardized how to do that. At this time, we recommend that people in Ubuntu, there's an easy way to turn off the suggestion that you do a major version upgrade. at which point you still see day-to-day operating system and support software updates coming down the pipe to keep your system up to date as a 20.04 Ubuntu. The 20.04 is what they call a long-term service release. So it's designed to be extensible, to continue running with security patches all the way up until 2032. Really at 2030 is when things would begin to stop being updated, when they would apply to security and other things that might compromise your system. Did that answer your question?
Yeah, so if I understand you correctly, then we should stay really at this 2004 version of Ubuntu.
For the time being, I think that if we can resolve the issues raised by moving to 22.04 with regard to getting RMS to run on it, we may have the option to do what is essentially an in-place upgrade. Your system's running 2004, and it would automatically, at your request then, update to 22.04. This may require some tweaks with the way RMS is installed on the newer release. By in-place upgrade, that would mean you don't have to start from scratch. Your existing system could be basically updated, which is something we cannot do with the Raspberry Pi. The Raspberry Pi, we need to essentially flash a whole new image, starting over on your storage media.
Yeah, okay, thank you. Clear.
Excellent. Well, thank you for the questions. We can definitely continue that during our Q&A, but let's first do a group photo like we do it every single year. If you don't mind, I'm going to ask everyone to turn their cameras on, and I will change my mode to the gallery mode, or maybe the immersive mode. Would that work? No. Let's do the gallery mode. Okay, I'm going to give everyone a few more seconds here. Okay, I see almost all are here, and I think all of them actually fit on my screen. I'm just going to give everyone maybe a few more seconds before I snap the pic. Okay, people are coming on, putting some clothes on, tidying up. Okay, how about in 10 seconds? Okay, it's probably all we're going to get. Everyone say cheese. Okay, there's the first one. And I'm going to save another one just in case. And here it goes, cheese. Okay, and there's the second one. Excellent. And that's saved. Okay, well, thank you all. And now I am officially opening the Q&A section / the unstructured workshop section. Every year I kind of joke that I don't know if anyone has seen Seinfeld, but they have something called Festivus, which is called the airing of grievances. So now is the time to do it. So feel free to complain and say whatever you want to say. If there's anything we can do to help you, if you have any questions about anything, that's something that we can definitely address. We can create a list of things that we can discuss. We have, I think, well over an hour, if not more. And if someone has any burning questions, I'm opening it up. If not, we'll structure it ourselves. I have a few ideas on mine. So, Keith, go ahead.
Yeah, I have a bit out of a box question. Due to computing a orbit from a fireball, we came in research about weather balloons. From weather balloons, I came to hunting down to recover weather balloons when they landed again. I'm now flying a pico balloon around the Earth, hopefully. And then I was thinking, okay, this pico balloon is flying on the Earth at about 11 kilometers high. what sensor I could add to this balloon to measure something that would help for the Meteor Society. It must be quite basic, lightweight, of course, low power consumption, etc. But it sees and quite a lot of balloons circling around. I noticed. So I thought, well, if we could find something simple to measure during day, night. Night is more difficult. Temperatures are quite low, but yeah, I was just hoping for some out of the box ideas.
Yeah, I mean, anyone can, just raise your hand, but I can just kind of list some ideas that I have. So if it's flying at an altitude of, 10, 11, 15 kilometers, as you said, humidity would be one good thing to measure. I think that'd be interesting, especially if we had long-term direct humidity measurements at those levels. And I think you can hook something up to an Arduino or something like that, but I'm not sure how accurate those measurements would be. I mean, other than that, for meteor research in particular, and what I was talking about, humidity is for most of our contrails, but for meteor research, we do always wonder what the wind speed is at those altitudes, and we use radiosonde measurements, and then we assimilate that using a weather model, and then we're doing all sorts of interpolations, et cetera, et cetera. Um, if we can get more information regarding that, I think that would be helpful. The only question is, how do you assimilate the data? How do you guarantee that the data is accurate, that it is calibrated in some sort of a standard format, and how do you ensure that it's included in the standard data sources that are used when those models are assimilated? I mean, usually when people release these balloons, the radiosonde measurements have a standardized format. You get added to the list of stations, and that's usually done at airports and done by weather services. That's a good question. I don't have much experience with that, but maybe someone else can answer. I see that Pete Eshman has something to contribute. Go ahead.
Well, based on a previous presentation, what about an infrasound recording device?
That's actually also a good idea. And one of the reasons is that infrasound can actually be channeled and propagated globally at a certain layer of the atmosphere. So you can position a balloon in that layer of the atmosphere. You will virtually be able to hear almost, infrasound signals globally. So that's actually an excellent idea. There have been a couple of people that came to me with a similar proposal. The only question is, how long can it stay up, and how reliably can you get the data down? And another question that I have then is, uh, filtering. Usually, ground-based infrasound. The sensors are quite big and complex. Some people use some special nets. Other people use very long garden hoses, because the idea is you want to filter out any high frequency signals. You want to leave low frequency signals. So I mean, if the filtering can be taken care of, I think that's actually an excellent idea.
Well, one of our members locally here, Tom Blog, is running an infrasound sensor at his house, and it is part of what's called Raspberry Shake, which is a global organization monitoring earthquake activity. And that means they're running his infrasound recorder is running on a Raspberry Pi.
Yeah.
So I think that might be an interesting avenue to research as to whether you could blend that in. Now, they run their own custom OS to do all that. In fact, we're running a 3-axis seismic sensor, which is another one of the options that you can look at from that organization. But they're also worldwide. So that means that they are gathering infrasound records worldwide already. It's just a matter of tapping into that. They want earthquake behavior, but I think it would apply to meteor as well.
Yep. So in fact, we did have a student who used Raspberry Pi Boom and Raspberry Pi Shake in his research to study fireball infrasound and fireball seismic signals. So data is there. One issue maybe was, I think, accurate timekeeping on some of the records. But other than that, I think it actually looked quite good. So yeah, I mean, ideally, you could hook up Raspberry Pi boom to a balloon and send it up. And if you can track its location accurately, you might get something out of it.
Yeah, if you stick a GPS module on the Raspberry Pi, I think you've got your location issues solved as well.
Yep, yep.
Yeah, that's the trick. All the balloons have a GPS module already, so that's the position is good. But of course the trick is to get the data down and to keep it lightweight and so on. But yeah, good. Humidity, I think that's the easiest one to get.
Mhm.
And I think most of them, what I see now in the community is if we are now the first flight is going with a pico balloon that can transmit also during the night. So they figured out to use a battery, charge it at daytime, and then can run it at -40 also during the night and sending down data, including to add humidity is quite easy. That's no problem at all. So if people looking for data for contrail research, then really they should look at this balloon community to find some data. So yeah, okay, but good points. Thank you.
Very exciting. Luke, do you have any comments about that?
No, that sounds like a good idea. Just don't hit any planes.
Yeah, I asked a pilot about this, real, yeah, not, yeah, a pilot which is flying airplanes. I'm always confused because I'm a pilot as well, but then no ships. But he said that a balloon is really no problem at all. It weighs less than 100 grams, I think. So it will not even scratch the paint, I think. So yeah, but I never heard a story about
That's
a
good.
balloon taking an airplane down. Only about sending rockets to a balloon flying over the US.
Right.
But there's another story.
Yeah, I always wondered about that. I've seen a few cruising at cruising altitude just zipping by. Like, oh, a weather balloon. It's like, I wonder what it would be like hitting one.
Okay. Yeah, but weather balloons are quite bigger. It is.
Yeah, yeah.
Yeah. But yeah, sure. I was also wondering about what a pilot would see if he's passing by. But yeah.
So if you're curious to see if it's ever an issue, you can actually install an ADSB receiver on board your
Yeah,
balloon.
that's
And
coming up.
you
Yeah,
can
but
monitor how close
yeah,
airplanes zip by.
yeah. Okay.
And that's fairly cheap too.
Yeah.
Or you could use the existing ADSB data set or have a local ADSB data set, and then you have your GPS coordinates on the balloon, and then you just look for close approaches.
Yeah. And then destroy the data if it gets really, really, really close.
Well, you're just gonna see it stop transmitting. So
problem is going to take care of itself. That's good.
that's right. Okay. Any other burning questions? Bob, go ahead.
Yeah, I have a question for Peter mainly. I guess I have 4 cameras on a Linux system, which is a Dell i5 computer, and I notice it's sluggish when I'm looking at the information on all 4 of the cameras, but they seem to be keeping up, and I'm typically not using it remotely. I'm not logged into it all the time. So is it common? Do you see sluggishness in your systems too?
I'm only running 3 cameras on my primary, and I have it set to display the live image automatically. All it really does is shows the last FITS file recorded. So they will change every 10.2 seconds. And I have not seen any overhead at all from that. Now, I'm not running show live stream because I don't like the idea of doing that during capture. I don't want to do anything to interfere with capture. The other thing you can do is you can set it so that it doesn't actually display that FITS file, but it's sitting there in the appropriate RMS data directory, which means you could just click on, I think, what's called live JPEG, and it'll pop up and you can just view it manually one at a time. I know you can spot check how things are going without having these images overlaying on the screen, the individual static images.
Yeah, I'm not watching the camera images. I'm just watching the logs roll by, the update information for the logs.
If I may chime in on that,
Sure.
So the way to tell if your computer is powerful enough to keep up with everything is actually in the log. And maybe I can share my log here and show you exactly what I'm talking about. So I don't know if you're running the GStreamer pipeline or the OpenCV pipeline, but so this is a log, and I'm using Klog. It's a software that's available for all platform, Mac, Windows, Linux. And I've got a log loaded here. And you can search for a particular keyword in your log with Klog, and it will isolate all these lines containing the keyword. And for example, I typed max. So all these lines are showing the max frame age and the number of cumulative drop frames so far. And the key thing is the max frame age. So it's how old the frame that's being currently processed is. So it should be fresh. So it should be like typically it's under 1 second. And then here you can see some hiccups. Like it's like, oh, it jumped up to 3. And here it jumped up to 4 seconds. Meaning that frame is very old, and it's so old that the buffer is full, and the buffer is dropping frames. I don't know if you see my mouse, by the way. I don't know.
I do. I see.
You do. Okay. So this in itself means, okay, it's keeping up. There's some hiccups. It's not too bad. It's mostly good. I don't know if I have an example of a computer that wouldn't keep up, would have very consistent high max frame age. So you would show consistently around 4 seconds all the time, and the drop frame rate would consistently increase. That would be a good indication that, yeah, your computer is overtaxed, not keeping up. But this computer in particular was like, okay, it's mostly good. There's sometimes a hiccup. Sometimes the hiccup is from a camera disconnecting, not from the computer not keeping up. So if you see max frame age that's consistently high in above 3-4 seconds, it means your computer is not keeping up.
Okay, I'll try that. Take a look. I have 3 of the cameras on isolated network just connected directly to the computer, and one of them is running through a router.
Right.
But I can look at them and look at these packets and see if the packet flow is consistent.
Right. If it's running the CV2 pipeline, it's gonna show a different number, but the concept is similar. It's I don't know if I've got one open here. Maybe this one. No. No. Oh, here. So this is the CV2 pipeline. So because CV2 in the CV2 pipeline we don't have accurate timestamps, we can't use that trick. But we can use another trick, which is to say it takes the computer about twice as long as the frame rate to process one frame. So if these numbers blocks max frame interval is consistently above 1, it's gonna drop frame. So this computer can't keep up, and it's constantly dropping frame. And the keyword for that is normal. I use normalized. So if the normalized number is above 1 consistently, no bueno.
Okay. Thank you.
And Luke, I think one of the comments you made is that we can see that if we look at the observation summaries that are available on the GMN status log, and you click on a given station and the tilde symbol, it'll bring up the observation summary, which will tell you the number of dropped frames over the course of the night.
Yeah.
And that's I find that's a hugely beneficial way of monitoring stuff. That and then a visual review of the FF interval plots will typically show also. If there's red in the plots, then they're drop frames and everything is correlated.
Right. You could have drop frame either because the computer is not keeping up or because there are connection issues with the camera. So if the issue is a connection issue, you're not going to see this high max frame age in the log. You're just going to see suddenly it drops.
Oh, that's great. I didn't know that.
Right.
What I've noticed is if I reboot the system, then it's running really well, but then sometime later it's not. So I was worried that maybe there's some memory leak here going on where temp files are building up or something eating up memory space. But I've looked at it under top and other ways to try to investigate that, but I'm not seeing it.
We are not seeing any memory leaks, so I don't think that's it.
Yeah, and I try to prevent that by running the GRMS updater program every afternoon, because that clears out all of Python. It runs RMS update to pull down a new code, restarts everything fresh. So even if there were a memory leak, it wouldn't persist from one day to the next to the next. It'd be a cascading building probably. Luke, Luke, one quick question. You said that the max reading was indicative. A high max frame means that there may be a Ethernet cable issue as opposed to a system issue. Is that correct?
No, not exactly. Let me show that again.
I guess what I'm looking for is a way to distinguish a camera network issue versus a processing machine storage issue.
Okay, so do you see my screen again? Like this is a GST pipeline. And we do have some drop frame, but if you look at the max frame age, it's consistently low. So it's keeping up. Except on occasion, let's see if I could scroll down. On occasion, there you have a drop frame here. And so if I click on it and see what has happened, maybe in the log here, I can see some indication that, yeah, there was a glitch in the camera. So it's not the computer that's unable to keep up. It's the camera has just had a little snafu here.
Okay, thank you.
And so the way to tell is that it's consistently low, except on occasionally it spikes. And I wish I had an example where it would show that it's consistently 4 seconds, like over many frames. That's an indication that the computer itself is not keeping up.
Okay, thank you.
Excellent. So one point of discussion that we can open up is probably the changes that were done to the code to enable daytime processing, daytime recording and processing and video saving. So there's a lot of interest in having RMS run obviously 24/7, but also record videos. So for those kinds of systems, we're no longer talking about very cheap Raspberry Pis, which run at the limit of their CPU power and memory. We're talking about maybe more serious systems that can take disk capacity and have a large disk space. So with the recently upgraded GStreamer pipeline, the way it works is we can branch off the video recording and the frame recording into RMS. So a part goes into RMS and another stream goes directly into a file on the disk, and that automatically gets chopped up into smaller pieces. That part, I guess it wasn't that hard to do, and that's working and it's operational. The hard part was accurate timestamping of the video files. The issue is that the video file gets saved to disk with no time information. So what we have to do is we have to pull the time information from the raw video stream where we have good timing information, and then we add that to the videos. So currently we have code that's in testing, which does that in real time. So when the video file is saved to disk, and it can be a 10 or a 30-second segment, it's automatically timestamped. And there are files, a new type of files called FT files for frame time. And these files essentially contain the frame number from the beginning of recording and an accurate timestamp. So that way you can compare the frame time from the beginning of recording when we're talking about from the beginning of recording, both for FF files and also for the video files. The video files also can automatically be cleared from the disk. And I think right now we've set a limit of 48 hours, but that can be modified if necessary. And the idea is that if there is a fireball or something like that of interest, full raw videos are available. And by raw, I don't mean they're still H.264 compressed. So it's the data that comes from the cameras. In terms of daytime operation, so the trick was to change the parameters on the camera using our camera control interface. And the camera control interface right now only supports this very specific protocol that the IMX291s are using. So that is not the general ONVIF protocol. It's pretty much baked in for this particular camera type, where at a certain sun elevation angle, we just swap the camera parameters. So I think the gain has changed and the way the camera responds to light and a few other things, and it's also switched to the color mode. That's done automatically. So the cameras that are not supported, I think, are some 307s, not all 307s. It really depends on the protocol, but it's in operation, it's deployed, it's working fine, and I think even in the current version, what you can do is you can turn on the video recording and you can turn on this 24-hour observation. But in the latest code update, which hopefully we're going to push in a couple of weeks, once all the bugs are ironed out, the time stamping of the videos is also going to be correct. So that's going to enable us better, well, obviously more coverage during the day because daytime fireballs are also going to be able to be observed. For now, we don't really have any plans to have any automated detection of daytime fireballs, with the idea being that if a daytime fireball happens, we're going to know because it's going to be big and it's going to be bright, and people are probably mostly going to hear it. It's definitely going to produce infrasound. So it's not going to be an event that we're going to miss. And hopefully 48 hours is going to be enough time for us to save the data. Now, thanks to Luke's improved astrometry method, where he found that we weren't taking care of a slight precession effect, the plays that are generated during nighttime should also be applicable during daytime as well. So that is something that is planned in the near future, and the feature that's currently also enabled, and what enables observing contrails, is that daytime nighttime switch. So even though video is not recorded, there is a new feature that's been rolled out on all cameras, and that is that a single video frame, not a stack frame, is saved every 5 seconds into a directory, and then a separate time lapse is created. And that way, everything that you see on that time lapse is no longer smudged. So you won't see individual meteors, but you also won't see, let's say, long streaks for airplanes or clouds or something. It is a normal time lapse, so to speak, as you would make it with your consumer grade DSLR or something like that. And on those kinds of videos, we can observe contrail as well, and also cloud types and a few other things. They're not good for sprites or something else that that is bright. It's not good for transients that only last for a short period of time, and where the background is static, but it's good for other things that change very rapidly, but they last a long time. For example, like cloud and cloud evolution and cloud type. And for example, one future avenue might be cloud classification. There's a lot of information, but I think the keys here unmuted himself. So do you have any questions?
Yeah, I have a question about daytime observation. Do you have to then increase your memory on the SD card, or what size is recommended then? Because I have now 256 gigabytes. Will
Yeah.
that be sufficient for one camera?
Well, you see, that's a good question. I don't have a good idea of how big a single night is. I think it's on the order, it's at least the same as one night of FF files, roughly. It can be a bit bigger. So you can think of it in those terms. So if you have enough room to fit a few more days of FF files, let's say 2 more days of FF files, I think that should be enough. However, the downside is, and for me, that's what I've been told. I don't have direct experience, but as far as I understand, SD cards don't like continuous writes like videos. They like writes which are in chunks. So saving the video, streaming the video to the SD card directly might kill the SD card. Now, that's what I've been told. And however, when I actually tested how the size of the video file updates. Even though GStreamer doesn't really allow us to control any buffering, I do see that the size of the video file only increases by about a megabyte to a megabyte and a half every few seconds. So I'm not sure that that continuous write issue is actually relevant for us. Now, if you turn it on and destroys your SD card in a couple of weeks, that might be the problem. But right now, I really don't know. I think we just have to test it.
And another potential issue with a 256 gigabyte card is that the it's going to compete with the Meteor archive. So if we need to go back in time to say, hey, we saw a fireball 7 days ago, the chance of that archive still being still being on the SD card is reduced. So 256 is currently a bit tight, I think, for 24/7 continuous recording. Unless you're comfortable with not having the archive file on Meteors more than 7 days, that could be fine. And also, there is a trick I discovered recently about reducing the number of I/O to the SD cards. So in Bookworm, the system OS cache is by default what's called write back. So it doesn't write to storage; it writes to memory, and if you lose power, you lose some logs. But it's reduced the number of I/O to the card a lot. And but there are settings that you can change on older version of the Raspberry OS to have the same effect, to switch it to write back. And I have a script for that I should share at some point to enable that. So that, I think, reduces the wear and tear on the SD card. So watch for a post on the group IO when I'm ready to share the script.
That's
okay.
excellent.
Thank you. Or is there maybe, do we have to switch to another system to stack all the files? There's not SD card, but like another hard drive, or what you call them.
Yeah, you could plug on a Pi 4. You can plug a USB drive, an external USB drive. That's a great cheap solution. If you have a Pi 5, the NVMe drive is the best. So that's fast. It's designed for continuous operation. Yeah. So do you have a Pi 4?
All my systems are running on a Pi 4, yeah. So 4 cameras, 4 Pi 4s now at the moment, yeah. So either like Pete says, if I want to upgrade, also to go to daytime capturing, so either I go to a Ubuntu laptop or Pi 5s. That must be then. But I think Ubuntu laptop will be also for the memory wise the best solution then maybe.
I think it's the
Or not.
best. I think it's the best solution and the lowest cost for multiple cameras. I just checked the video files directory on US 0001, which is running continuous and with video save on. And that directory was 43.9 gigabytes, which it's a single day. As I recall, there's only a single day's worth of data. So that's a significant amount of video. Now, without video, if you're just talking about saving frame files continuously day and night, then the overhead is much smaller. It's on the order of, what, 5 or 6 gigabytes for 4 days worth of frame summaries and 1 day worth of frame data. Did I get that right, Luke?
Yeah, that sounds right.
Okay.
Well,
So
you can try and turn it off if it doesn't work.
Yeah, okay, but for me it's clear. Yeah, thank you.
So on the config files, there's a setting for how much space you're willing to allow your camera to use. And I'm thinking, is this all coordinated together for both day and night
Yes.
usage of that space? Because I've choked that space back just to try to make sure I had extra space on my drive because of the other issues I was seeing. And
Well,
it limits my history information, but it still keeps me going.
Yeah, keep in mind that that value is for a single camera because that's in each single camera's config. So you want to multiply whatever margin you want per camera by the number of cameras and then set every config to that value. So if you want 50 gig per camera and you got 4 cameras, and each config file says save 200 gigabytes of data, essentially. Since they will evaluate it sequentially as they start. And one problem is that value is too small. You'll wind up with one camera sacrificing all of its old data in order to keep enough space available, instead of distributing that sacrifice among all your cameras. I don't know if that makes sense, but
yeah, I think I did do that. I think what I want to do is just turn on one of my 4 cameras to daylight also and walk it up one at a time and see what happens.
That's what I've done for now. I only have one of my 3 cameras running. And that particular camera is pointed very high, about 75 degrees or so. So it's covering a whole bunch of sky directly over the Albuquerque metro area. You know, that window is basically picking up a whole bunch of potential contrail information pretty much at zenith or close to zenith. And I figured I'd just do one to get it started. I'm thinking about adding a second of my 2 cameras because I have another one also pointed very high, slightly to the north of this one camera. And they only overlap by about 10 degrees in field of view. I guess my thought is if I'm doing that, then other cameras in the Albuquerque metro area probably don't need to bother with monitoring for contrails. Luke, have you given any idea to the distribution of recording devices and the space between them?
Yeah, we don't have firm numbers yet. Like in theory, I assume in a very, very clear atmosphere, 100-kilometer base should be sufficient. In practice, we don't know yet. If we need to reduce that to 50, we also don't know how much gap in observation we can deal with. So if we see a contrail leaving the field of view of one camera, we can compute its movement. It's called dry advection over time. So it could drift into the field of view of another camera, and we can fill in the blank. but we don't know the exact numbers yet. So I think right now a conservative number, 100K base would be good.
And ideally, each of those positions would be monitoring all cardinal directions plus overhead. So it would actually be, for instance, a 5 or 6 camera multicam setup at a single site.
Yeah.
And then if those are separated at a grid of 100 kilometers, then you'd have your ideal coverage.
Yes.
Thank you.
Yeah, I mean, in terms of the coverage for contrails, one thing to keep in mind is that it's so much smaller than for meteors because the height is about, factor of 10 lower. So the coverage for contrails, I think it's probably Luke, can you maybe pull up your map that you have?
Yeah, I got it right
With the flight
here.
levels, yeah. I mean, probably the UK or just England specifically is well covered. Everything else has huge gaps. Yeah, so what
Alright.
flight level is that?
So this is let's do in the middle here. Let's do 350.
Okay, so that's roughly 10 kilometers.
Yeah. So that's, for example, that's my camera. That I've got 6 cameras and 4 of them are pointed fairly low. So I have a lot of reach. Those are the lowest camera. They're not pointed as low. Also 6 camera systems. They don't reach as far. So in the UK, yeah, we are covered.
Yeah.
Pretty much.
When you say pointing low, are you talking about 35 degrees, 45 degrees? What do you mean by low?
Mine, what's the point? Oh no, I can figure it out. So the bottom edge is reaching down to 10 degrees elevation.
Okay.
It's
So
45, so they pointed at 35, I think, yes.
about 35. Okay, thank you. That was a target we were looking at for
Right.
6 camera systems. So.
And still working on the project here, the 6 camera project. Now the latest is that we would print the prototype here and then have a laser printer in China produce a bunch. But now with all the tariffs and the drama, I don't know. We'll see what happens.
Okay.
Probably produce something locally, yeah. But yeah, so in terms of contributing to the contrail research, a lot of the cameras are still not swapped to the daytime mode. So Luke, you did show me some really nice stats and some graphs. Do you have that handy? I think we did mention that we want to show that at the meeting. Okay, somewhere in the email, if you don't mind. Trying to find it quickly.
Yeah.
But yeah, so nighttime observations are beneficial, and it's funny because all other contrail cameras, as far as we're aware, anything that's been published, they've mostly been done during daytime. So Paul, you did I don't know if Paul is still here, but he asked about the effort of Eurocontrol. So yes, so in fact, the folks at Eurocontrol did develop their own camera systems and they did deploy them in, I believe, the Netherlands, but they were only observing over during the day because they were not sensitive enough. They had issues with calibration because they couldn't really use star fields. And calibrating these kinds of cameras is very, very tricky due to their massive distortions and complicated model. So really it's that big problem that RMS solved. And now the question is, can we just switch to daytime observations as well? And the answer is yes. So that's the only thing that needs to be done. Just that daytime switch needs to be turned on. Now nighttime observations, I think they are beneficial, but the thing is the number of flights overnight isn't really that high. Most of the traffic does happen during the day. So all the nighttime observations would have you would have evening and morning traffic, but pretty much overnight, the amount of traffic is very, very low. That's why generally daytime observations are I wouldn't say more desirable. I think they're as desirable as nighttime observations, but I think there's more traffic during the day than overnight. That's for sure. And the good thing about our cameras is that they are reasonably IR sensitive and visually sensitive. Oh, there we go. That can see contrails quite well, even though they're not that well illuminated. Um, okay, so one thing that Luke did is he made some wonderful plots showing the number of cameras over time and some sort of an attrition rate. And he also has a list of cameras that do have the daytime mode turned on and a few other things. So I'm just gonna hand it over to Luke to tell us about all this.
Yeah, so this is just the number of cameras reporting daily over time. So there's about right now, I think 10,024 reporting daily over time. I'm not too sure what the dip was about.
I think we had some sort of a bug that took some cameras down.
Yeah. So that's the daily reporting. There is about 1,180 cameras actively reporting. They just that it seems that on every given day we have about 100 random cameras not reporting. So that brings the total down a little bit. So I've got some stats of those. As far as who is using GST versus CV2 backend, so we have about 90% of the cameras are now on GST pipeline. They all have the weblog enabled, so that's good. About half of the cameras are also running some sort of external script. Not sure exactly what that's about. About 99% of the cameras are running a resolution of 720p. So we've got about 1% of oddball running 1080 or other video formats.
And how many do we have on the Pi 3? I think it's like 24, 26.
So that's another email. That was 20. Pete, I sent that to you. It was 29. I think 29 are running Pi 3s.
Pi 3s, yeah. So out of, let's say, 1,000, we only have less than 30 running the Pi 3. And I just want to reiterate what we're planning to do, and that is to officially drop support for Python 2 starting on July 1st this year. And the way that's going to work is we're going to take the working of the version of the code, we're going to create a branch called Legacy Python 2 or something like that. And then going forward, we will not be constrained by all the Python 2 limitations. And it's actually getting hard to even test the new versions of the code on some cameras. And it's really preventing us from kind of pushing forward. But whoever's still operating the Pi 3, they should be able to switch to that branch. Unfortunately, it will have to be a manual switch, but it's literally just running one command in the terminal. And that way the code will not change for the Pi 3. But the expectation is that hopefully at some point in the future, all of the Pi 3s, or at least all the images that are running Python 2 are going to be retired because these systems are, I mean, honestly, a security threat because they haven't been updated in probably over 5 years now. So that's something that should be handled. And if you are running a Pi 3, try to make arrangements to upgrade to at least a Pi 4 in the next 6 months or so.
And then finally, about 40 cameras right now are running the 24/7 same frame capture.
Sorry, how many?
40.
40 cameras.
40
so that's how many?
That was as of last week.
Yeah. So our idea is, sorry to interrupt here, Luke. Our idea is that whoever wants to run daytime observations, they can. If you do want to do the switch, that's great. After a period of testing, we are thinking about enabling this by default globally. That should not break your cameras if it's been tested enough and if we know all of the edge cases, but it's going to significantly help to contribute to the project. Now, again, I'd be very happy to hear about any pushback, but we are doing extensive testing, and it would be good if you at least try to do it manually yourself, and you can always then disable this feature in the config file. So right now, if there's nothing in the config file, it's disabled by default. But at one point, if there's nothing in the config file, it will be enabled by default, and you'll have to manually turn it off if you don't like it. I think there was a chat message here. Daria asked a question that nighttime control observations would be more important due to their much greater impact on warming. So yeah, so nighttime, well, contrails overnight do prevent the troposphere from cooling and dumping all that heat into space. But that's not the point. The point is that we have a complete set of observations that can be used to constrain the atmospheric models so the forecast can be better. So the idea is to have the completeness of the data set and not target individual contrails. So here the idea is that not we wouldn't observe aircraft directly and then someone would call the aircraft and say, oh, go down. That's not how it's going to work. The idea is we're just going to have a comprehensive data set and it's all going to be done in the forecast. Now, at some point, if the loop is fast enough to have real-time observations, so we can see, okay, here's an aircraft, it's producing a contrail, it's not supposed to be doing that. RMS does contrail detection, does live reporting, and then that gets fed into the machine, and then they decide what to do. That would be great, but first cut, I think there would be at least some sort of at least time delay between would not be a live feedback loop. That's for sure. Okay.
One more stat, if I can.
Absolutely.
And that's the biggest problem, the pebble in our shoe right now. About 15% of our stations are not updating themselves automatically anymore.
Mm-hmm.
So we have 15% of station, I think 160 stations at this point, out of date. And so they're going to need to be manually updated. Still a little unclear as to why that happened. I did drop off a script last week that unfortunately was not ready, so I should not have done that. And I apologize if it caused any problem. I will try again and have a script that will automate getting a station back up to date with as little headache as possible.
Yeah, so I think in most cases, these are either Linux installations that are not being properly updated because they don't have the script properly installed, or some sort of a custom installation, or something happened on the Pi. The SD card is corrupted, or the repository broke in one way or the other. But again, I think that most of those are related to the SD card not behaving appropriately, or something happens during the repository update, for example, like a power cut, and it's some sort of a broken state, and then it just doesn't update itself correctly. Those are some things that I think require manual attention from the operator, or I think a lot of us would be happy to help with that remotely. But yes, that's something that needs to get updated. Hopefully, that's something that we could add to the observing report, and then that's something that the weblog can be updated with and have a little status message. So I think it would be a good idea to have, if there's a specific warning or a status message in the observing report, we can communicate that via the weblog, so it's not really hidden, it's all fully transparent. Gene has his hand up, so Gene, go ahead.
Yeah, I wanted to circle back to the underlying concept behind this contrail research. And my understanding is that since these contrails are formed in regions of the atmosphere that are already supersaturated with respect to water ice, our existing network of weather balloons maps out those areas at some scale. So we already kind of know, or should know, where those regions exist based on conventional meteorological measurements. So so is the contrail work then aimed at sort of filling in the gaps between the pi ball locations? Is that what we're doing here?
Yeah,
Yeah.
so oh, sorry, go ahead.
Well, very briefly, I mean, I'm not a contrail expert, but from what I've seen and read the papers, is that the prediction accuracy using the current models and the current data set that exists is very low. And we're talking about, 20 or so percent, 15 to 20%. And I've also seen when I chatted with the folks from Eurocontrol, they showed me a map and they say, look, these are the contrary predictions using the Google model, and you see a bunch of splotches on the map. Great. Now we switch back to, I don't know, the French atmospheric model. It's like it's a different combination of splotches on the map. So different models give different answers, and they're all incorrect in different ways. And the major issue is the data set that we have right now is not sufficient. We need what we call ground truth data set. This airplane is producing a contrail, yes or no? And that's it.
Not every area of the sky that is supersaturated with respect to water ice will produce a contrail if an aircraft flew through it. Is that what you're saying?
That is correct. Yeah, there are other factors like wind shift. So as the contrail ice crystals in the contrail precipitate, it matters what environment they find underneath themselves. If there's a wind shift, it's going to start spreading. If the region that they are precipitating into is also supersaturated and there's a wind shift, it can spread. So yeah. And regarding the weather balloon, so there is is it 4 times a day? Something like 4 times a day there's a weather balloon. Don't quote me on the 4 times a day.
Well,
There
it's
are
usually
weather
2 times a
balloon
day, like midnight and
3
noon,
times. Thank you.
depending where, but yeah.
Yeah, so there are weather balloons sounding that are both not very precise in the spatial dimension and the temporal dimension, and also they're not very precise at the altitude we need them to be precise at. So they are not taking enough samples at the cruising altitude of aircraft.
Well, that circles back to Pete's question about a camera on the rear of the aircraft, but I'm thinking about a frost point hygrometer on the front of the aircraft where you would measure the humidity on the aircraft and know whether you're flying through a parcel of air that's supersaturated with respect to ice or not, and then you have some better sense of whether or not your exhaust trail is forming a contrail or not.
That is a long-term plan, is to equip a fraction of the fleet with those sensors to fill in the gaps.
I thought aircraft already had those sensors in place. They don't.
No.
They do.
Just a handful of test planes. I think Lufthansa has got a few. Hawaiian Airline had a few helping the research, but we're talking about maybe globally less than 50 airplanes or something like that. So.
Thank you.
And Luke, if I have a question for all the models about contrails, do they take in account what happened at sea level? Because the last few years, there's a major change in how shipping is going around the world using low carbon fuels and ways to keep running on the dirty fuels, but running other systems to sort of clean the fuel. I can show you a picture, but
yeah,
is going on. I hope I have to figure out how to share it at one moment. And then you see what I mean.
That was so they had an interesting problem because they cleaned up the emission of shipping boats, which reduced the cloud coverage at low altitude. But low altitude clouds are warm and they're very reflective. They actually apparently maybe more cooling than warming. Definitely not the case with high altitude clouds that are definitely more warming than cooling.
No, but I'm not sure if you can see the picture, but
yep.
Yeah, but anyway, but they look like old steamboats again, like 100 years ago. But yeah, this is only one, but they're going around for thousands of them, of course. So yeah, I don't know. I just was wondering if that's Yeah, anything to do with all the modeling and if that makes.
I mean, there's some overlap, like in the issue of condensation nucleus. So they are trying to clean up aviation fuel so that it doesn't produce as many or different size of particles, so that the contrails dissipate faster or don't form at all. So there are efforts on that end too.
Okay. Now I'll try to get it away again. Oh, one moment.
There's another effort that's going to be happening probably at some point in the future. Now, the focus of the effort is just to, get contrails, get some observations, say, here's the airplane, here's the contrail. But at some point in the future, I've been talking to some atmospheric physicists, and they're interested in classifying clouds and detecting clouds that we see. And that's also something that can also go into tropospherical weather forecast models and improving them. Because right now, again, the data is very scarce, especially if you want to map a particular cloud to a certain height, that remains challenging. And we also have to have a good understanding of our detection efficiency of contrails. So for example, overnight, that's easy because we have our star detector, and we're already doing that for meteor flux, where we determine our observing periods, essentially when we can see stars and not see stars. But during the day, we'll have to have a completely different approach, where we'll have to define what clear skies mean, and understand whether we are detecting or not. But I think we'll have to combine that with some maybe satellite imagery or something. Maybe that might be an easier approach, but it's a difficult problem, but we are uniquely positioned to solve it. So, and many good things can come out of it. So.
Okay. Hey, Dennis, I've thought about, we were talking about weather balloons, and I noticed there's a huge database about the position that the balloon's going up, but also when they are recovered on the ground.
Okay.
And so there are a lot of volunteers trying to recover all the weather balloons when they landed. So all this data is available. Could this be helpful to sharpen the dark flight models, because it's coming from more or less the same height, 30 kilometers high. Of course, it's not acting like a meteor, of course, but you can calculate I think Bastiaan de Vet is that doing in Delft with this, what do you call that, this simulator to figure out the CW from a meteorite. So if you have this CW figure from this, well, this payload coming down, you can maybe calculate back where it should be landed, where it is found, etc. And yeah, this data is really available.
Yeah. This sounds like a great project for a student in atmospheric physics who's trying to refine the wind models in the upper atmosphere. From our meteorite recovery perspective, we are more, let's say, users of those models. We download the model, we run the model, we sample the model, and we kind of trust whatever's happening behind the curtain. I can't say that I have much experience in actually tweaking the parameters of the weather models. That's not not our expertise. It's definitely not an expertise of most people who are interested in meteorites. I think just a handful of people in the world even run weather models on their own. And myself, I'm reliant on the Australian group to provide that kind of model, because they have it installed on a supercomputer, and every time there's a meteorite fall, I essentially tell them, here's a location, here's a time, and take some time to run the supercomputer, do all the model fit and the data assimilation, and then they produce a result. That is the extent of my knowledge and how I use the atmospheric models so far.
Yeah, but I meant something different. It's about when this weather balloon is going up to predict where it's coming down again, where you can find it. And this prediction you can fit with the actually found position. That's what I meant. So they have a prediction. It's coming down from 30 kilometers high, but they found it on this position, blah, blah, blah. And so That's what I thought. Maybe it has some coincidence with the, what do you call it, some overlap with the dark flight models.
Yeah.
That's what I
Yeah.
was thinking about.
Yeah. You see, it might actually be possible to do this by using the data that it takes when it goes up. And you take the same measurement and try to model when it's going down. The equations are quite simple. I mean, you could quite literally take a dark flight model and program in the density and the rough shape of the object and just release it and see where it ends up. Yeah, I mean that's a good idea. Yeah.
Okay.
Yeah. It's definitely something
Yeah.
that's possible.
And do you know also about a project in Hungary where they're going send up a meteorite in a balloon to drop it down and to see with sensors inside?
No, actually, I was not aware of that. So that's it's pretty. I mean, I know of projects where they wanted to do something a bit more extreme. So there was, I think, a private Japanese satellite which wanted to create fake meteor showers. So, for example, for the 2020 Tokyo Olympics, they were supposed to be shooting meteors above the Olympic venue, but that never happened. And I think that would be extremely interesting from modeling perspective and compositional perspective and observational perspective. Now, if you could, for example, if let's say Artemis 3 was to happen and astronauts are coming back from the moon, and if they were to, before the braking deceleration phase, if they were to just stick their, hand out of the window and just release a little rock and let it go before they decelerate, I think that would be a very exciting exciting project. It would probably be very difficult to predict where it would end up, but the speeds would be sufficient to actually simulate the real meteorite entry. So.
So I have another question about this turning on this flag. I was looking for the flag in my config file and I don't see the flag there. And I know that earlier in the week you posted that list of people, Luke, about people that were out of date. And I actually was out of date. I was running like an October version. So I did the upgrade and I believe I'm current now. Did that process also modify the config files to include this section for the flag?
No, the config file is never automatically modified, so it would have to be manually modified. So if an option in config file is not present, it's assigned default values by IRMS. So the
So I have to go find a
settings.
new config file someplace and then scrub it to match mine, I guess.
Well, Pete has got a solution.
Well, actually, yeah, Steve Matheson shared a script that he wrote that you can run manually that will take your config file and the new template that's sitting there in source RMS after an RMS update and compare the two, and it would basically merge your values into the new template. It wouldn't replace the original config file. It would give you a candidate you could use to replace that config file. And I ran it on all of our systems here in New Mexico, and it worked extremely well. I was very pleased with it.
We should add it to RMS scripts, I think.
I think so too, because it doesn't force you to change your config file, but it provides you the option to update to whatever new parameters have been created since you last looked at it. And for some of our cameras, honestly, and also remember that there's a section in your log file that echoes everything that is in the template, but is not in your config file. And it can be a huge number. That's the first thing that keyed me into the growing discrepancy between a config file that might have been started, 2 or 3 years ago, and what a modern one is today.
There's actually a config audit report generated at the end of every day. So it's in the archive folder. Look for config audit. And it's going to show you all the options that you're missing in your custom config file, or if you have options that don't do anything because they're not supported, it should tell you that.
The thing I like most about Steve's script, merge script, is that instead of you arbitrarily adding these parameters, if you run his script, the resultant config file is now in the same order of parameters as the template, which means you can begin to look for these settings in a predictable place instead of randomly scattered throughout the major sections of the config.
So I would find his information on the RMS reflector. I just need to go search for that. It sounds like.
Actually, I think that's what Luke's discussing, is that what we need to do, if Dennis thinks it's appropriate, is to actually begin distributing that utility script along with some others that RMS are distributing. For instance, there's one that updates buffers that many people don't know about. That's perhaps valuable for fixing a log warning about your buffer size isn't big enough when you're running GStream. And that's right now, that's sitting in source scripts, I believe, source RMS scripts, I believe. And so we could add Steve's utility script into that so that it would automatically distribute to all the stations. It would be up to the user to run it. So we're not forcing it on anyone. Does that sound like a plan?
I absolutely agree on all of these. So again, the general policy of the GMN was to never have the config file being automatically updated by RMS. However, if that was done in a semi-automated way with the operators, if the operator is doing it consciously, then that's fine. One thing that I would hate is to have, let's say, a remote station and then the config file gets updated automatically on its own and it just goes down and it's down for a very long time. That's definitely not what we want. So yes, if there's a script, the config file can be updated in a single step and it's backed up and it's done manually, that's perfectly fine. Yeah. And yes, a comment to Bob is yes, it doesn't show up there because the config file is never touched by RMS. All the interventions need to be done manually.
Thank you.
Sorry, Luke, you said oh yeah, there's no option to record day only. That's right. Yeah. Daytime recording is an addition to nighttime recording. And during the day, FF files will not be generated. The detector will not run. The only thing that will be collected are those 5 second or those video frames taken every 5 seconds, from which a time lapse is going to be generated. Or if the video saving is enabled, then videos will also be saved during the day. But again, for that, you need more space on your either SD card on or your machine. So we don't have that many stations that are running that at the moment, but that is the direction we're moving towards. And I think we are setting the cameras to the color mode, so the videos are also going to be in color. Pete, go ahead.
Yes, a question about the video. Obviously, that's another setting. Save frames is one thing, but setting record videos is totally different. And that's the one with a major storage space impact. So these video files at present are only residing on the station. They're not uploading to GMN? Question mark?
Nope.
Okay.
So they're not. And the idea is that they would either be picked up manually, or we've also implemented that if there is an event monitor request, they are going to be uploaded to the server if event monitor requests it. So that's the idea, right? We know it's there and we don't want to upload huge amounts of data. So we only pick it up when we need it. I do have a student who's working on a kind of a, we call it a fireball detector. It's more of kind of a fireball alert system based on the total brightness in the image. The work is still in progress, so hopefully we're going to see something implemented or not. Might take a couple of student projects to get there, but the general idea is to have some sort of a more of an automated approach, or at least have a set of potential candidates that can be investigated manually, if nothing else. Yeah. That's the general plan at the moment. Many things happening behind the scene, and I actually forgot about one thing that I wanted to show. I forgot to put it on the list, but let's first answer a couple of more questions, and I'm going to play a video, pre-recorded video. So, Pete, go ahead.
Yes, I have a new topic question.
Go ahead.
This has to do with the event monitoring system.
Mm-hmm.
What is the mechanism today that puts bright events into the event log? And what is we as something like an area coordinator, if somebody's looking out for a handful of stations,
yep.
What do we need to do? What's our role in this? And how do we get something entered into the web log?
Okay. Yes. So currently the user interface is pretty much non-existent. The user interface consists of an account on the GMN server where you log in and you manually edit the text file with these entries. And once you edit that text file, the stations are going to pick that up and they're going to upload the data to their station directories. And that is also going to be resident on the Pi itself. So the station operator always has the fireball files. They never disappear when they're down, where they're deleted, whether or not you issued the request or not. And then what you have to do is you have to manually pick up those files from the server. Now, all of that can be done with a couple of scripts. I mean, I usually use like rsync or something like that. So again, the user interface is you pretty much need to have a good grasp of Linux and know how to do these things. So if you're coordinating some stations and you would like to have that capability, we can definitely organize that. But with the understanding of that, it's still pretty much very manual. Now we could develop more features and write more scripts so things can be added in a kind of an easier, more transparent way. Or for example, anyone can put like some sort of a file in their special directory and that automatically gets picked up and then automatically things get downloaded and distributed. It can be done just right now. These are not the current priorities. So if there is an event of interest, we can definitely post that, send an email, and it'll be taken care of if you don't want to go through the trouble of writing Linux scripts.
Okay, so for most of us then, if we think we just saw something that might be a dropper, really needs more investigation,
yeah,
we should at least post something to the GMN forum as an alert and then request that be looked into.
For sure. Yeah, absolutely.
Okay, thank you.
That's the bare minimum. Again, there's some coordinators who already have their hands on, the actual can actually post the request. So that's fine. If there's anyone here who is a coordinator who would like that and who's Linux savvy, please let me know, and we'll give you access.
Thank you.
Awesome. Now, okay, there's another item, as I said, I forgot, and a lot of effort has been put into creating a custom star catalog. So, as you might know, the current star catalog that the GMN uses, the Gaia DR2 catalog, lacks bright stars, which is not good when we want to calibrate on bright stars, which the GMN mostly sees. An alternative is the Bright Star Catalog version 5, which is good, but the problem is that the magnitudes there are in the V band, but the GMN magnitudes aren't really in the V band, and it's also lacking a few other things. So this work was mostly done by David Rowlandson and one person that works with us, Connor Martz. And we do have a first version of this catalog, and I think I did post something on the group. Connor recorded a short video that I will show now. Unfortunately, he couldn't be here today. So you'll see what the current status of the GMN Star catalog is. So let me just share my screen, and if you guys can't see it, if you guys can't hear it, please let me know. Okay. I think this is gonna do the trick.
Hello, everybody. My name is Connor Martz. I am the newest member internally here at Western University, working internally with the Global Media Network. And I started a little bit before the new year, and my main task so far has been to basically create or finish up a new star catalog, which would replace the old one that we load into SkyFit. Let me just share my screen here, and I can share my slideshow. So, what was the reason for this? Well, the main motivation obviously was the fact that we don't have a lot of bright stars in the old catalog, right? This catalog is, primarily Gaia. Well, it is Gaia, right? The default one that loads into SkyFit, and it's because it's Gaia data, it's heavily biased towards the fainter end of magnitudes, right? So we're only going to be seeing the fainter stars, which leaves out a lot of the bright stars. And for meteor physics and meteor astronomy in general, what we need is bright stars and faint stars, right? When we're making calibration plates, which are, the way we actually track fireballs, which is, the meteorites and stuff we recover, it comes from those. We need to be able to accurately track where it is in the sky. So we need calibration plates for that, right? And a source of annoyance for me, especially having made a few hundred of these now for different stations and just improving the network overall, is that there isn't any bright stars at all included in Gaia. I mean, well, obviously there are some, but there's not a significant number that would be useful. So sometimes you'll load up an observation and you'll see almost no stars at all except the bright ones. And frustratingly, these aren't included in the Gaia one for the most part. So that was one of the main reasons that we wanted to reconcile this, and we wanted to create a new catalog that, included bright stars and faint stars, but it also provided higher accuracy in terms of astrometry, right? Because we're going to be using proper motion corrections, and we're going to adjust for that stellar drift over time. And you can see here in the plot here, we have the limiting magnitude of all the stars in the catalog plotted against the cumulative number of stars, right? And you can see there's not too many here at the brighter end, 0 magnitude, but around, say, magnitude of 12, it plateaus and kind of just, like I said, plateaus. The main reason for that is that when we were selecting Gaia data, we selected this as our cutoff. And we don't really need much fainter than a magnitude of 10. What you'll notice in SkyFit is that you'll almost never, ever be below a magnitude of 9, right? So, well, above, you know what I mean? It won't be fainter than 9, in other words. So for this reason alone, we also split the catalog up into 2 different files, and I'll talk about that in a second. But the other thing I should mention too is that we include multiple magnitude bands for photometric reasons. So get a lot of different information from the catalog. And other things it might include as well are, spectral classes, object types, like whether or not it's a binary, single star, stuff like that, identification codes, and other things as well that might be useful. And for faster loading purposes to use in SkyFit, we've also split the catalog into a binary format. So it reads really, really fast. And to make it even faster, like I said before, we split this up based off of magnitude as well, right? Like if you want the whole catalog, that's fine, you can get that. But for the most part, we don't really need, for SkyFit purposes, we don't need a magnitude much fainter than 9. So that's our cutoff for this. So the ones that you'll see inside your Pi are actually going to be the catalog that is split off from the limiting magnitude of brighter than 9, in other words. So, and this may not be relevant, but if you want to actually just directly download it, you can get it from the website or load it from the GitHub itself. And the relevant line here in actually using this in SkyFit is in the configuration file, just kind of control find star catalog, and then you'll see this line right here. You just need to change this to GMN underscore star catalog, just like that, and then it'll load when you start SkyFit next. And so, yes, the results. So as you can see here on the left, that's the newer GMN star catalog, and on the right is the default Gaia one, the one that loads by default without changing anything. And as you can see, well, it may not be that obvious because, there's a lot of things going on here, but you can definitely see around some of these brighter stars that we have no star in the Gaia catalog, but we do in the newer one, right? And that's useful. It may not be useful in this case because, we have so many faint stars here, and that's not really may not even be necessary to use the bright stars, but it's nice to have. But the main, I think one of the biggest, most profound impacts of this is that, at least for the 4mm cameras, we do see significantly better fits as a result of this. I hope not. Yes, anyways, so let me get this out of the way. I'm sorry. So yeah, so on the left here, so this is just a 4mm camera. It's stationed in the United States. What I did is I opened it up with the old catalog and the new catalog, and I fit the exact same stars. And I'm just showing you, highlighting, and maybe this isn't the best, say, configuration for the default star catalog, but I'm just giving you a rough kind of comparison between how these two, the differences in the stats, right, from using these two different catalogs. So what you can see here on the left is the new GMN star catalog, and it has significantly better fit results from the root mean square deviation. And again, for statistics, we want this to be as close to 0 as possible for this to be really, really good. So obviously the one on the left is significantly better on the one on the right, 2.5 times better or so. And that may not be the case for all the cameras, but it's definitely seeming like it's the case for the smaller 4mm cameras. And that's obviously and most likely due in part to the inclusion of proper motion in actually estimating these. So what's next? Well, as you may have seen from this plot here, we're still missing some bright stars, right? I mean, if we look, actually I can see one right here. If you see this cluster of 3 right here, there's one missing on the left here that was included on the right. So interestingly, even though we've done a lot of work to include as many bright stars as possible and to reconcile this, there's still bright stars that are missing. So we'd like to kind of invite you all as a sort of a community to help us identify these stars and add them to the catalog to make this as complete as possible. So the easiest way to do that is if you can just, identify what the star's name is, and then just send an email to Dennis or myself. I'll show my email again at the end, or Dennis can probably explain that for you guys or pass that on to you. But essentially, if you guys can just, pass on the name to us, I can easily add that to the catalog, and it won't be very difficult to include in and reconcile that. So, email me, cmarts@uwo.ca if you want to contact me directly. Connor Marts is my name. Let's stop sharing. So yes, it's been a pleasure. Thank you for listening, and I am looking forward to watching the video and learning more all about your projects and everything that you've been doing to contribute to the Global Media Network. Thanks a lot. Bye.
Okay, well that's Connor's video. And the update about the catalog. We did notice that a few stars were missing. We do have some duplicate stars, so hopefully in the next couple of weeks to months, we're going to have some sort of a semi-final version, and we're planning a small publication about this. And yeah, so the features of the catalog, I think one thing to Connor, I don't know if he dwelt much on it, but yeah, we have UGRI, no, BVRI color bands, and we also have the Gaia G, Gaia B, and Gaia R. And the proper motions, which don't make a huge difference, but they make enough of a difference, especially for astrometry on longer lenses. And that's pretty much about it. I mean, it's the completeness down to magnitude 12, and those color bands and proper motion is really what makes this work. And if you're asking why we're doing this, the answer is, find me another catalog that has all this, and you'll be surprised how hard it is to find a good bright star catalog for our purposes. It's just that there aren't any. So yeah, any questions about this? Pete, go ahead.
Yeah, apologies if I missed this in Connor's presentation, but my understanding right now is that this change to our config file for the new catalog is only going to affect things when you run SkyFit 2. It doesn't change the normal day-to-day recording. I'm not, can you clarify that?
Yeah, so this catalog, in terms of the astrometric accuracy and a few other things, I'm not sure you're gonna see huge effects. So, we're talking about, you know, what we have right now is reasonably well averaged, right? Um, and the catalog would have to be manually changed in the config file. So if you're using Gaia now, it's perfectly fine. No changes necessary. This is just going forward for some, accurate work and for completeness. And at some point, we're looking into improving photometry, especially, Damir is focusing on stellar photometry, and he also found how can I put it, a good ratio of those color bands to match the GMN magnitudes, and we find a significant improvement of, I'd say, a factor of two in the photometric accuracy. So, okay. So, sorry, Jamie, go ahead. You have a question.
Yeah, question about the star catalog.
Yeah.
When I'm doing plate power files, I find the thing that really messes them up is double stars. I don't get an optimum fit unless I take all the double stars out of the star selection.
Yeah, so this catalog actually does have a column of like probability of it being a double star. So that's something that we're planning to introduce. So one thing, I don't know if I don't remember him saying, but you also have common names of stars, spectral classes of stars, and a few other things. So the idea is that we modify SkyFit in such a way that it marks double stars, and it also changes the color of that marker depending on the spectral class of the star and a few other things. And we generally find that stars that are really red, their photometry is a bit messed up, but all other stars fit quite well. It's definitely work in progress. Now we have a base to work on. Okay, Michael, you have a question?
Yeah, just check on. I think you answered it. I was just going to ask you about the IR filter and the lenses as soon as we've removed them, but I think you've answered it there on the red stars. Thanks.
Yeah.
And I'll just add there. I mean, while that presser was on, I just logged into my Pi 5 and I see it is already in the config file, so it must pushed out already. Thanks.
Yeah, that's awesome. Yeah. So again, the catalog is there, and the way we split the catalog into two. Stars down to magnitude 9 are already in RMS included, and the file is about 18, 19 megabytes, which is really small. If you want to push beyond magnitude 9, another version of the catalog is going to be automatically downloaded from the GMN site that goes down to magnitude 12. Because that file is 250 megabytes. So even though it's only 3 magnitudes, that's where most of the stars are. And I think that most people will never need more than magnitude 9. So that was their general thinking. So yeah, 20 megabytes is manageable, 250 is not. And in fact, GitHub has a 100 megabyte limit in terms of file size. So that's what we had to do. Yeah, I see there was a. Okay, so Jesse, could we get an option in Skype to switch to use catalog to this? Yeah, I mean that's a good question. That's done upon loading. We could add it as some sort of an input parameter or something like that to override the catalog. The only downside is the spectral bands. So the Gaia catalog only has the G band. So okay, that's fine. However, if we only load this catalog but use the spectral bands that are already in the config file, those are appropriate for the Sky 2000 catalog, which we initially thought that those spectral bands fit best. That ratio of spectral bands fits best to GMN data, but Dummer has found that in fact we can do much better. So, I mean, do we use a spectral bandstand or not? The question is, do we care about the photometry or not? Like honestly, I would do it right instead of do something partially. So my message would be right now, just leave things as they are. I'm not sure that having those bright stars is actually a big hindrance on calibration. In fact, what I found is that bright stars can sometimes saturate. And if there's a tiny bit of coma or some sort of a weird PSF, the centroid of the bright star is actually bad. And if you try to include it, it does not fit well. So you should try to avoid using very bright stars in your solutions because just the simple the pick accuracy is so poor because it's really big, really wide. It's saturating in the middle. It has like coma, so it's kind of pushing the centroid to one side. My suggestion, just skip the bright stars unless they're absolutely necessary to make your calibration. Okay. Any more questions about the catalog?
More just a general one, if you don't mind,
Yeah, of
about
course. Go ahead.
how to estimate if I have an image, say the a FITS file, how would I estimate the magnitude of a star on that file, on that image?
Oh, okay. Maybe I don't know if Damir's around. He can talk about his procedure, but you can do it in SkyFit. You just switch to the manual reduction mode, and as you know, if the way you would measure a point on the fireball, you just do the same thing on the star.
Okay,
That
perfect.
that,
I'm
that should
thinking in particular about TCRB and whether that will,
Yeah, yeah. Although I think the background, you see, that actually might not be true because the background in SkyFit is subtracted. So any objects that stars should actually be removed. Um, so how would you measure it? I mean, you could potentially load not the FF file. Um, When you could, you mean the existing calibration, right? Um, we haven't thought about that. I guess we can add a new feature in RMS that does measure stars. I mean, the way Damir does it is he relies on CalStars, so the information that's already in the CalStars file, which does have the amplitude, well, sorry, not the amplitude, but the total intensity is there. The magnitude isn't, and then we apply the calibration to that, and we apply the plate to that, and that computes the magnitude. That's an interesting idea. I guess we can slightly modify SkyFit to allow that, to allow measuring stars, because right now it's going to subtract the stars, and you're just going to get well, pretty much nothing. Ideally zero, because if it's not changing from frame to frame. Yeah.
Okay, thank you.
Yeah. So Keys, do you have a question there?
Yeah, about the star catalog. For the initial calibration of a new camera, let's say, mostly to start in SkyFit to make the plate, it will be helpful if you can start with the bright stars to have a rough estimate where your camera is pointing. And then for the real calibration, as soon as you have done that, then you swap to the catalog with the faint stars, and then is that an option to add in SkyFit too, that you can easily swap between two catalogs easily?
No, but with the new catalog, you don't have to do that anymore because you have both the bright stars and the faint stars. And if you only want to see the bright stars, you can change the limiting magnitude of the catalog. You can press the R and the F buttons in SkyFit, and it's going to remove the faint stars. So if you just raise the limiting magnitude, that's
Okay, so clear. Thank you.
Yeah. And it's going to be much helpful because you can see the constellations and the patterns, which are much easily recognizable, which, unfortunately, those things are missing in the old catalog. The stars are just too bright for the instrument. Yeah. Okay. Any more questions?
I put one on the chat just now.
Go ahead.
I have a question, if I could. One of the theories that I remember hearing is that the moon was formed due to an impact on the Earth, possibly. And if that's so, then it seems like to me it would have created a significant debris field. Would that be totally gone from gravitationally stirring and
Oh, for sure.
just, yeah. So
Yeah,
what? So then that makes me wonder
it was
how long,
recreated back in. Yeah.
how long does a debris field last if it's created? Uh, it seems like there would be a decay rate that would be known for meteor debris fields.
Oh, for sure. I mean, there are many papers that were written on the topic and numerical simulations that were done. I don't have the numbers off the top of my head, but the early solar system when this happened was very dynamically chaotic, and all of those debris fields have been cleaned up a long time ago. And pretty much everything that we see in our current solar system, for example, all the meteor showers and most of the sporadics and dust, all that is actually quite young. We're talking some meteor showers are only a few 100,000 years old. The dust environment itself, we're talking about hundreds of thousands of years to a million or so, but not much longer than that. So most of it is actually quite new. And if you look at what are called the CRE ages of meteorites, so which means when they were detached from their parent bodies, so it means that they participated in some sort of a giant impact. Again, we're talking about hundreds of thousands of years, millions of years, not much more than that. So everything that we're seeing pretty much coming to Earth is dynamically new in terms of their ejection from their parent body. Of course, asteroids are the main belt asteroids are pretty much fossilized from the formation of the solar system, so they are kind of the oldest unchanged material that exists in the inner solar system. And if you really want something old, then you have to go out to either the Oort cloud or the Kuiper belt, and that stuff there is most certainly extremely old, which we can actually see when we look at their surfaces. Well, we have measurements of surfaces of only a few of those objects, like Arakoth, but you can see that its surface was actually pretty old because of the colors and the surface processing that can be measured from those observations.
Okay, thank you.
Okay. Well, I think I'm gonna slowly wrap up this first session, and we're gonna have another session starting in it's about 2 hours. I believe so. So now is 9:55 p.m. UTC, so that's 21:55 UTC. And yeah, in about 2 hours, we're starting our second session, mostly for folks in Australia and New Zealand. And we're also going to have some talks by people in North America. Now, what I'll do now is I will leave and rest. But if anyone wants to stick around, and if you guys want to chat some more, I will leave the meeting open. So thank you for coming. It was a pleasure.
Thanks, Dennis.
Okay.
Thank you, Dennis.
Thank you.
Yeah, thank you, Dennis. See you next time.
Thank you.
Thank you all.
Yep. See you in a bit.
Are you visiting the Netherlands in the IMC meeting, what do you call it? Late this year?
Oh, sorry, you're asking me?
Yeah.
Oh, unfortunately, I won't be doing much travel this year, so unfortunately not. I won't be. I don't think I'll be coming to Europe this year. Maybe next year. We'll see, depending on where the IMC is.
Right.
But you should
Okay.
definitely attend if you can.
Yeah, if I can. Yeah. Okay. All the best.
Thank you.